Welcome back to the Introduction to Machine Learning, ML100 workshop. This is our lecture number 2. This is Thursday, I believe July 21st, I would imagine. Now, am I getting that date right, or is it 22nd? 21st, 21st. Okay. So I'll just do a very quick review of what we did last time. Last time we went over the course modalities. We said it's a 6 weeks course. We all agreed that we will divide the Saturday into 2 pieces. We will do the theory on Thursday evening, and we are going to do the lab on Saturday morning, California time, which for people in Central time becomes a little bit harder, 9 p.m. to 12 p.m. at midnight. And Saturday morning is perhaps better noon to 3. And for people in India, it becomes 7:30 in the morning Friday, which is what it must be there at this moment, till 10:30. And then the Saturday night, 10:30 to 1:30, which will be a little bit harsh. But we live in we are a global class today, this time around. So there'll be a little bit of adjusting from all of us that we have to do. Now, 6 weeks of theory, labs, homeworks, quizzes, paper reading, social learning, and projects. So there are many aspects to it, folks. Try to benefit from all the aspects. Please take help from the teaching assistants. I hope if you have, those of you who did reach out to the teaching assistants, you hopefully were pleasantly surprised how accessible we all are. We are always there to help you. And as I said, we do have an emergency number. Just as in the United States, you can call 911 if there is an emergency. If in machine learning you have an emergency, call us at 1-855-LEARN-AI. We'll be there. Anyway, well, jokes apart, we talked about machine learning. What is machine learning? Why do we use the word machine learning and not artificial intelligence? It's because we don't know what intelligence is in a very quantitative way, except to say intelligence is present when you see any entity learn, right? And learning in its simplest form, in a more quantitative form, is first to have a measurable way for errors or for the performance of a task, and then to see measurable improvement in the performance of that task, right? As the machine learns, or as the human being learns, or the entity learns. If you can quantify the error and you see a reduction in error, you say that learning is taking place. There is a broader definition of learning, which is that learning is the ability to generalize. We took the example of cows and ducks and children in the meadow, in our meadow, and that will be our own special support vectors meadow, in which there are only cows and ducks and children trying to understand cows and ducks. Now, in that, when a child begins to make less mistakes about whether an animal is a cow or a duck, and for those of you who just joined, the example is framed as follows. There is a meadow, a simplified meadow, in which there is a pond, there's grass, and so forth. There are some ducks roaming around, and there are some cows roaming around. And you are there with children. You show the children an animal, and you say, look, this is a duck. It has a beak, it has webbed feet, it has feathers, it's small. And then you show it this big animal, and you say, look at this big animal with this swishy tail, horns, right? And so forth. And that's a cow, the 4-legged animal. So you keep doing that. Now the children, and then you ask the children, you show them an animal they haven't seen before and ask, what is it? Is it a cow or a duck? If the children have not figured out what a cow or duck is, they will make mistakes. They will make far less mistakes the more they get a sense of what a cow or a duck is. Right? Now, what we do is we show specific instances of cows and ducks. So one easy thing that a child could do, and some people have photographic memory, they may not understand a cow or a duck at all. They may look at the 10 examples of cow that you showed and memorize them, and the 10 examples of duck that you showed and memorize them. If you show them exactly that cow or duck, they'll get the answer right. But if you show a new animal, then they won't get it right. Right? Then it is evidence that the child has not learned. It has just memorized those instances, right? Instance memorization. We do it all the time. If you go back and look at your college days, there are courses that you learn from, and then there were courses that you hated. So what did you do? You just memorized the important questions, which you hoped would come in the exam and you passed. Right? So that's the difference between memorization and learning. So if you were to look at the distinction is learning. When learning takes place, there is a generalization from examples. You generalize, you form a concept. For example, as a child, looking at the duck gets the grasp of what a duck is, the duckiness of a duck, right? And likewise, the cowness of a cow, the essence of a cow, what it is. A concept forms in the mind of a child. It's a generalization from the instances. So another way to look at machine learning is the ability to generalize, and generalization is another way to think that it is intelligence. Right? We talked about the fact that if we look at this way, it is a quantifiable way to measure learning because we can. It's great. It has one thing though, it is agnostic to whether the entity that learns is sentient or not, is alive or not. Machines are equally capable of learning as sentient beings, right? Fishes learn, humans learn, right? Dogs learn, and machines learn. All of these things are capable of learning. From there onwards, we moved to a little bit of a history of the field. We talked about the legendary mathematical physicist Gauss Legendre, who did the work. The first paper on this was Legendre's paper, 1805. Before that was Gauss's paper, 1793, but he did not quite articulate the method of least squares. Legendre did it in a very explicit way. To understand this, for the case of regression, of predicting a number, we took another story. This is the story of a young entrepreneur trying to sell ice cream on a beach. The young entrepreneur sees that if you have a warm day, more ice cream sells. If you have a cold day, not so much ice creams sell. So the entrepreneur plots the data and then realizes that there is a linear relationship between the temperature and the amount of ice cream you would sell. Now, why would the entrepreneur want to know that? Because if you have a ice cream shop on the beach, you buy ice cream from a wholesaler. If you buy too much ice cream and it doesn't sell, you lose money. If you buy too little ice cream from the wholesaler, well, then your customers are turned away and you have no ice cream to sell them. So you do that. So when you do that, you need to find what is the real relationship between ice cream and temperature, ice cream sold in temperature. When you plot the data, the eye may indicate that it's sort of a linear relationship, but in higher dimensions or more complex data, you may not know. Now, you make a ground, excuse me. You may make basic assumption that the relationship is linear. Assuming that the relationship is linear, the relationship can be represented by infinitely many lines, right, of different slopes and different intercepts. So which of each line represents a hypothesis? So we talked about two things. We talked about the real space and the hypothesis space, and we talked about quantifying errors. So one way to compute the error is obviously very simple. What is the gap between your predicted amount of ice cream sold and the actual amount of ice cream that was sold? That is the error gap. Now you take the error gap for all the data points across the different temperature values and somehow aggregate those errors to get a composite total error. Now, when you aggregate the error, you have to be a little bit careful because yi minus yi hat, the delta in error, could be positive or negative. You have points above the line and below a line and the actual points. So sometimes you overestimate, sometimes you underestimate. So if you were to just add up the errors, you run the risk of ending up with zero error because it's symmetric sometimes. So you're looking at the size of the error, not its direction. So to erase the direction, what you need to do is you need to take its absolute value. But when you take the absolute value, the question remains, there are many ways to look at the absolute value. I can look at the absolute value. I can look at the square of the absolute value, its cube, its fourth power, and so on and so forth. So why a particular way of aggregating? There's so many ways of aggregating the error. So what people do generally, if you take the zeroth power, that won't work. If you take the first power, in other words, if you just add up the absolute values, like in this equation here, if you just add up the absolute values, then this equation we are referring to, if k is 1, then it is the sum of absolute error, SAE, right? So let me put a word, SAE. And if you take k is equal to 2, it is the sum of squared errors, right? Now, sum of squared errors, these two are the most commonly used measures of error when we are trying to predict a number. In other words, when we are doing regression, right? So generally, because you want the error measure to be invariant of the data set or sample size, so it is common to take the average to divide the answer by 1 over n. When you do that, the sum of absolute error becomes mean absolute error. It's mean of absolute errors, but the more technical, the correct English, I suppose, would be mean of absolute errors, right? So EI 1 over n. But people just, it's common for people to forget the off and so forth, and people just call mean absolute error instead of errors, though more technically is the mean of absolute errors. So it's just a language that has stuck, right? So this is it. We talked about the sigma. We also talked that it is far more common to use the squared errors. Why we do that was another result that was discovered more than 200 years ago by Gauss and Markov. It's the Gauss-Markov theorem, often popularly called the blue theorem, a best linear unbiased estimator theorem. I'll come to that theorem, which basically says that in general, you're better off with a mean squared error. Not always, but quite often. In well-behaved conditions, you are quite better off with the sum squared error. And one thing that I didn't quite do is to give you the intuition of when one should use one and when one should use another. In this world of data science, data is the king. Quite often the situation determines which of the two methods is better. And this is one of the things you will learn in machine learning, that a priori, so I'll use the word a priori quite often. A priori means before you see the data. A priori, you can never theorize and say one method is better than the other. Are we together? The data will determine which of the valid methods turns out best. It's called the no free lunch theorem. We'll come to it one day. But generally, the mean squared error is more popular because it tends to work better more often, and that's the Gauss-Markov theorem. But in other circumstances, it is the mean absolute error. In fact, one of the homeworks that I'll give you, I'm about to release it, literally shows you different data sets in which different error measures work better. And you have to develop the intuition why one works better than the other. But I'll give you an intuition. Many of you are parents here, right? And many of you, and all of us have been children who have been parented at some point. So one of the advice that people give, I don't know, it is, there are many words to it. Somebody once gave me a very interesting name. He said, it's the benign neglect principle of parenting. It says that don't hover over your kid and point out every mistake. You know they're making mistakes. They're up to mischief, right? So if they're particularly quiet, it means they're up to some real mischief, right? If you ever see toddlers quiet, you're in trouble. So, well, okay, they're up to some mischief and they're making some errors. And this is true as a teacher also. A bad teacher will point out every mistake, right? A good teacher or a good parent would ignore all the minor mistakes and look the other way. But the moment you make a bigger mistake, then invest a lot of energy, either parenting or teaching, right? That becomes a teachable moment. Right? So there is something like that. I would like to believe that maybe that's a real intuition why the mean squared error tends to work better, because what it does is most of the time the errors tend to be small. If you have a line that really goes to the data, most of the data will be close to your line in 2 dimensions. So your errors will be small relatively, right? So the squares will be small. But what happens if a number is bigger? The square is huge. For example, a 2 square is 4, but 20 square is 400, right? It's drastically bigger, isn't it? It's drastically bigger. Or 9 square is 81. It gets exponentially bigger. So when you're learning and you're trying to first minimize the big errors, right, effectively, you quickly zoom into the right location through the data. That's one way of saying it. But the problem with this is that when the data has outliers, specific outliers, then those outlier points, which are actually mistakes, they dominate the learning process. Do you see that? If you square the error, then the big errors, the outliers, the data points that are far off. What are outliers? Data points that are far off from the other data points, standing away from the other data points, that will dominate. So imagine that you're looking at data like this. Most of the data is like that. And somebody has made a mistake and there is a data point like this. Now, normally, ideally, you would like to say, you would like to draw this line and consider this a outlier, this outlier as either an anomaly or something like that, anomaly, and just ignore it. But if you just do some squared error and you're not careful, this point will dominate the learning. Are we together? And it will lead to a line that is perhaps like this, which is suboptimal, isn't it? Or maybe even this, I don't know. We'll have to do this lab to see how far it goes. In fact, it is one of your lab homeworks. Do you see the point, guys? Right? But generally, when you have outliers, they tend to need special treatment. And in the case of our entrepreneur and ice cream, something unusual may have happened on that particular day. Maybe a whole school bus came to the beach, right? And you had an extraordinary amount of ice cream sold. So it is a special case. You don't want your machine to learn from that data point. In fact, you want it to be not overemphasized, if at all, right? So that is the problem with just using mean squared error. It becomes susceptible to outliers much more. Whereas when you just take absolute value, then you're keeping things in proportion to the error relatively, right? So that's a distinction between the two, right? So we come now to regression. So the word regression comes from regression towards the mean. Now, today we will talk about that, Galton's paper, regression towards the mean. And what is the cause of regression? So we learned that there's regression, there's classification. We focus on regression now. Galton found that children, offsprings of extraordinarily tall parents, tend to be a little less tall, and children of extraordinary short parents tend to be a little bit taller. I believe he first saw it in peas, then he saw it in humans, and so on and so forth. He noticed that it tends to be common in biological phenomena. So where does it come from? So that brings us to the concept of the irreducible error. Irreducible error quantifies that which you don't know. For example, when you sell ice cream on the beach, and as an entrepreneur, you're trying to model it as a function of temperature, there are other things you are not considering. For example, given the same temperature on a weekend, you would sell far more ice cream than you would sell on a weekday. Weekday parents are working. They can't bring their kids to the beach. And weekends they can, holidays they can. So even a given temperature, there would be an error band depending upon what day of the week it is that you can't do. So factors that you don't know, they represent themselves as irreducible error. Even when you have the best method, the best hypothesis, still you have residual error there. The other source of such errors is quite literally instrumentation error, right? So this happens all the time, by the way. I carry from US a pretty good measuring scale with me, so that when I travel through different countries, I know what the weight limits are in different airlines. And I always stay about 4 or 5 pounds below that. But whichever way I do, I know that there are certain airports in certain countries who have a weighing scale that will always declare my suitcases to be overweight, no matter what. Right. So what do you have? You have genuine instrumentation error by design or not. You have instrumentation error, right? And then those of you who stand on the weighing scale every day know that if you stand on the scale and then 20 minutes later you stand on the same scale, you magically your weight changes. How many of you have seen this? Right? So we see that all the time. So you have instrumentation error. So those are represented in the irreducible error represented by this epsilon symbol. Now, yeah, go ahead, Albert.
So Gauss invented the SSE or MSE? Or both?
The same, they each, one is just 1 over n of the other. So now, so I must just say that in passing, that while regression towards the mean in the particular case of human beings happens, that children of very, very tall parents are less tall, there is also the Flynn effect. Don't confuse with that. Flynn effect says that every successive generation statistically is taller, brighter, more capable than the previous generation. What is today the Olympic world record? In a few years, high school kids would be doing it as their records, right? And we can see it. Just look around at some of the high school records and go back and look at the Olympic records for 25, 30 years ago. And you would see that high school kids are beating the records of 30 years ago. That has to do with the fact that we are all better fed, well protected, right? Well taken care of. Technology has advanced, longevity has increased. The human body doesn't go through as much wear and tear and so forth, right? So that is a different thing. But at the individual level, regression towards the mean happens. So why does it happen? We realize that it happens because there is always a irreducible error. So suppose you have an extraordinarily tall, so imagine that a person is very, very tall. It will be a function of genetics, namely, let us say some genetic causative factor based on the grandparents' height, right? So grandparents would be tall, but there would be the irreducible error, which will have a bell curve. If by happen chance, this error, whatever it is, whatever the child was fed, the mother was fed, whatever, things that you can't account for happened, caused a parent to become excessively tall. It means have this huge epsilon added in the positive direction to the causative height. Then what would happen when that parent has children? You cannot assume that the same random phenomenon, the same random forces would cause even more height increase, isn't it? In fact, the error is likely to be smaller. But when you take the causative factor plus a smaller error, your actual, the child of the parent now has become shorter than the parent. Are we seeing the reasoning, guys? No? So that is what it is. Then we learned about gradient descent, a pretty interesting concept. So there we talked about the dual space, the space of the real data and the hypothesis or the parameter space. For every hypothesis in the real space, a line, a linear relationship, there is a point in the parameter space. And for every point in the parameter space, every hypothesis, we have a certain amount of error. We looked at the error and we realized that those errors, they form a quadratic equation. Remember, we expanded it out and they were a quadratic equation and they're greater than 0. This quantity is a square of some numbers. Sums of square is by definition greater than 0. And our intuition tells that because of irreducible error, it will be certainly greater than 0. Its shape looks like this. Whichever point in the hypothesis space, it achieves the minima, the optimal point of error, that is the best you can do. It will still be, this is your irreducible error that you can't get rid of, right? This bit of height. you will still have. Now, the question is, suppose I make a random guess. How do I find a path from here to there? So there comes the next part or the next crown jewel of machine learning, namely the gradient descent. So what it says is there is a concept of a gradient, which is a generalization of the derivative. It is represented by this inverted triangle, and we won't go over this because you can review the video. So, but for people who are new, please take out time with either me or the TAs, and we will walk you through that. If you have the gradient, the magical thing with the gradient is, if you think of functions, for example, this is a surface, this is a landscape, hypothesis space, this is a error surface rising over it. The amazing thing is in the function space or field, mathematicians have a built-in Google map of sorts forever. If they want to go home, namely the point of minimum of a function, all they need to do at that point is take out this magic compass, which doesn't tell north-south, but it tells which way is the gradient pointing. And whichever way the gradient is pointing, go the other way around. Walk opposite to it. And if you keep walking opposite to the gradient, you will essentially reach home, right? But you would reach home only if there is one home, there's one minima. If your surface is what is called convex, right? So this is a convex surface. Now you say inside is concave, but if you look like this as convex in common language, but actually the way mathematicians think, they look at this surface as convex. They say any surface is convex. Like this surface is convex because if you take any 2 points and you connect any 2 points with a segment, then the part of the surface that is there between these will always be on one side of the segment, right? So this is a convex surface. On the other hand, this is not a convex surface. Why is that? Because the curve goes back and intersects the segment, right? So we talked about that. This is non-convex. And we need to remember that, non-convex. So one of the problems in machine learning is that how do you learn or how do you go to the minima when the surface happens to be non-convex? And we talked about this. I believe I showed you some highly non-convex surfaces. Where was that? Maybe I'll type it in again. Let me do that. That it turns out that in machine learning, you don't always have convex surfaces. Yes. So I would just like to show you. We talked about this surface that in machine learning, quite often you get lost surfaces like this, error surfaces like this. Well, I'm using the word error and loss interchangeably, but there's actually a subtle difference, and we'll come to that. So this is the minima here where my mouse is. Can you see where my mouse is? We want to reach here, but along the way, there are many traps, there are many ridges and valleys, little valleys around this surface that you can get trapped in. So one of the questions is, how do we do that? And that brings us to the whole architecture and machinery of this beautiful subject. We'll deal with it. It also answers the question, why can't I set dy dx to 0? In calculus, in high school calculus, you learn that I can set just the dy dx to 0 and get to the minima. Why do I need to do this gradient descent? The reason for that has to do with the fact that if you do it, you'll find that there are practically infinitely many points at which dy dx is 0. Horrendously many points, right? And so that won't serve you. You need a systematic way to take you to a minima. Now, in the case of linear regression, the beautiful thing with linear regression is one of those cases where your error surface is really like a bowl, right? It's convex. So you can say, I could have set dy dx to 0 and found the optimal point. And that is actually what is done. In practice, when you have linear regression libraries, they do a direct closed form solution. They don't actually do gradient descent because you know for sure that if there is a point where the error vanishes, it is the right answer. Right? So you do closed form solutions. We talked about all of that, right? And so remember that gradient always points up points in the direction of maximum ascent, steepest growth, right? And if you want to climb up a hill, follow the gradient. If you want to go quickly into the valley, go opposite to the gradient, right? So that's the journey, right? And I illustrated this with an example in one dimension. If you take this function, and I'll just quickly review this, you have a function. This function, if you look at this point, the slope is negative. Why? Because when you take a small positive step, you fall. The function decreases. Decrease in function means negative slope, because slope by definition is the amount of increase in a function for unit step forward. A tiny, but by the way, unit step, not in terms of giant, don't take giant steps. Unit step means, imagine a millipede, right? Making with its tiny legs, making one tiny step forward. So when you take one unit tiny step forward, how much did the function increase? That is slope. If it decreased, well, that is a negative increase, and so negative slope. So at this point, it is positive. B, it is positive. At A, it's negative. But if you want to go home to the green point, what should you do at A? At A, you should go, if you want to go here, you want to go again in the, if this, because the slope is negative, you want to move forward, positive amount you want to add. So you want to add a negative of the slope. Scale down by a factor. You don't want to take a giant step, you take a little bit of a step. This is called the learning rate. Right? And remember, you are a little millipede or centipede. You're taking tiny little steps. Right? Likewise, at B, also it turns out that the same thing works, because you want to go in the opposite direction, you would do a thing like this. And so the net result is, it turns out that this equation and this equation are exactly the same equation. And so this becomes the celebrated equation of gradient descent in its simplest form, right? And what is in one dimension true, it is true in higher dimension, right? So if I were to write it as a vector, I would write it as next is equal to x minus alpha gradient of x with respect to x. Right? But we are not in the X space. Now let's go to the parameter space. So in the parameter space, you would say beta vector, beta next, is equal to beta minus alpha, gradient of the error surface, right? And gradient of the error surface, right? And this is actually the machine learning. This is how machines learn, by taking tiny step, not in the real space, but in the hypothesis or the parameter space. So this is the celebrated gradient descent step, right? Folks, I hope you have reviewed the video or you have watched the video. This is important. This is therefore the summary of what we learned the last time. Any questions before we proceed?
Just ask if I may ask, do we maximize the learning rate to get to gradient descent?
No, it turns out, oh, you mean the alpha, right? The alpha learning.
The alpha.
You don't maximize. There is a problem that happens. It's a very good question, and we are sort of jumping the gun. We'll do gradient descent in great detail at some point. But let me show you what happens. If you make giant steps, you see me making giant steps? What happens? Am I reaching the minima?
No.
No. So what happens is, if you take giant steps, if you are a Bigfoot, you won't reach the minima. You'll just be hopping all around the minima, isn't it? So that's the problem. That's the reason you don't keep your learning rate too big. But then, on the other hand, if you keep it too small, you'll be creeping your way towards the minima, isn't it? So one of the very, very interesting topics in machine learning has always been, what should the learning rate be? You can treat it in the beginning courses. In this course, you can treat it just a hyperparameter of the model, or play around with it, see what works. But there is more to it. As you advance, you go to ML400, you'll realize that this is a whole topic in itself. It's called the rate schedule, learning rate scheduler, and there are very powerful and intelligent theories on and methods on how to adapt the learning rate at different stages of the learning. right? But we won't go there. At this moment, just assume that you have to choose it judiciously. You can't make it too big, too small.
Hey, Asif, if I can ask a question. See, when you reach the minima, how do you know if it's a local minima or the global minima? You wouldn't know if you take just tiny steps. At certain point, you have to take a little bit bigger step to see if you can jump over the hump.
That is indeed true. And now you're getting into complicated things. So remember, we are, first let's crawl, walk, then run. So
Okay.
that principle, but your question is very valid and very deep. The thing is, in the case of linear regression, there is only one minima. If you reach the minima, you're done because there was only one, right? But when you get to more complicated surfaces, like for example, when you get to a surface like this, the question becomes more interesting. How do you get out of a local minimum? How do you even know that you're trapped in a local minimum? And what do you do? And there are beautiful, beautiful methods to it. Some of it coming from actually statistical physics and material science, simulated annealing and things like that. And we will deal with that. But for that, wait till ML400. You are 3 courses away from it at this moment. Yeah? We'll come to that in due time. So at this moment, Raj, for the sake of this course, just assume that if the gradient vanishes, you're home.
No worries. Thanks.
Yes. Any other questions, guys, before we continue?
Yes, if so, what if the curve was reversed? Like instead of y equal to x square, let's say y equal to minus x square, where there is no global minima or local minima to start with.
Oh, see, here's the thing. Suppose you have a function like this. Well, in machine learning, you won't because error loss functions are usually positive. But suppose you have a function that we say gx, right? So instead of minimizing, what you can do, this is a maximization problem, right? Or just take minus gx, you'll end up inverting g, and it will now become a minimization problem, right?
Got it.
Just change the sign and we can. So in machine learning, and traditionally most of these libraries, for no particular reason, these libraries are all tuned to minimize functions, knowing that if you ever want to maximize, take the negative of it.
Got it.
That's it. Yeah. So that is that. So guys, any more questions? Because now it's my turn to ask questions. All right, so I'll ask you this question. I'll tell you a fact and tell me what do you think happens? So pay attention to this, guys. At one time in my neighborhood, there's this University of California, Berkeley, right? Their sports team in their infinite wisdom decided to do something unusual. So now when you teach people, one of the first things you are taught, you learn, I mean, you internalize as an educator, is to give positive feedback. We know that as parents too, to children, we should give positive feedback. When they do things right, we should let them know that they're doing well. We should be rather reserve negative feedback for exceptional occasions, not often, minimize that, right? So not everybody agrees with the theory. Some people believe that that is coddling the generation and spoiling the young, right? There are old sayings like spare the rods, spoil the kid, and things like that. In various cultures, something or the other is there. So there's an alternate school of thought that says nothing helps so much in teaching people anything, whether kids or grown-ups, as a good, nice stick to whip people with, right? And you have seen that. You have worked for many managers who use that, who are always using a whip to scare people into working or being productive, because they feel that is how you improve people. Now, like people have different ways of looking at it. The overwhelming scientific data, it turns out, is in favor between these two different hypotheses. It is in favor of positive feedback, positive reinforcement, right? Now, that is what the data says. But people, obviously, nobody has to agree with the data, right? We live in very interesting times when data may say one thing, but somebody else might believe is the president or won the election and whatnot, right? So you see that in the US. So there was one group. Some people always feel that being strict is the right way. So the sports team decided here that every time a player does badly, they're going to absolutely rain down on that person and just thrash the tail out of that person. Not physically, but metaphorically, just rain down on the person and see if things improve. Now, and then they reported that, well, they found that if they rain down on the person or the players, the next day those players did better. Right? This is a real thing, by the way. And so they got so excited with their finding, they thought they had some very good finding. They went so far ahead as to publish their results. So, and this is what I heard actually, and which is ironic considering that Berkeley is one of the best places to do mathematics. Then a similar story is associated with Israel's Air Force. So you have Air Force pilots, the training pilots who train you, or training instructors who train you on how to fly a plane. Now, usually flying a plane, when you are doing that, it is a bit of a high stress activity. No matter how many hours you're spent in the simulator, when you're actually in the cockpit of a fighter jet or a plane, then it's a different game. You're in an airplane. You have an instructor next to you and you're flying, and you make too many mistakes and the instructor may die with you, right? So it's a bit of a tense situation. And so people were flying and learning, and so they decided that now one instructor decided that what they will do is enough of coddling. Anytime a pilot flies badly or makes a lot of mistakes, they will absolutely rain down on the person. Are we together? And what they noticed is that led to extraordinary results. They tabulated the results, and what they found is every time they shouted at a guy, the very next day, the performance of the guy improved. Clear data. They too published their results. That's how we know about it. Now, so how many of you would vote and say, yes, that is the way to do? And now is the time to bring out that stick and walk up to your kid who has been annoying you. Right? Or I'm joking, of course, don't actually do that. How many of you would subscribe to the theory that giving very strong negative feedback was the reason or causes better performance the next time, or actually leads to improvement in performance, or is the cause of improvement in performance? Okay, how many disagree? Go ahead. Somebody is speaking. Hina, go ahead.
Yeah, Asif. I don't know. Does this mean that it improves the performance by coming to a local minima and not we never reach the global minima?
No. Forget about minimum, maximum. Forget your mathematics. Just think in basic sense. How would you argue? Imagine you're in a court of law or you're talking to common people. Which way are you leaning? To give positive feedback, or there is actual value in giving instant negative feedback?
We would never know until we compare it to even better performance. Does a positive reinforcement lead to an even better performance? We would never know until we compare it to a better performance.
Yes, and thus spoke the journalist amongst us. Very good. Anybody else?
Yeah, I believe that it depends on the activity, but if you are inventing something, then negative feedback is not going to help. The encouragement will help there. But if you are going to do a repetitive job, it only needs to be tuned better, then probably this will help.
Okay. Good point. Anybody would like to come up with a counter argument to these things? Like, for example, anybody can prove can you point out to what is the flaw in this line of reasoning? Anyone? Articulate it well. Hina, you did it partially. Yeah, fear of losing employees is not good enough. If you know in your heart that you should thrash them, but you're not thrashing because they'll leave, that's not a good, that means that they will not, in your view, they'll never develop, they'll never grow.
You need a consistent study that accounts for all the factors, not just that one time with the.
Yes, a consistent study, all of you are saying, that accounts for many factors. Anybody else would like to hazard a guess? Guys, this is the time to use your imagination, come up with explanations. Speak up, please. It goes to the heart of what we are going to talk today.
Another thing, what was, or how many things changed? Was the talking the only thing that changed?
Yes,
Or
that's the only factor. The student pilots did badly. They were called into a room. They were absolutely, given a piece of the instructor's mind in very uncertain terms. And next day, their performance improved. Kate.
Do they have all the instances where they had poor performance, no feedback or positive feedback, and then what the performance was?
Yeah,
the next day?
Kate's thing is that did we also look at the case where some poor performance were given no feedback or positive feedback, positive reinforcements, and what happened to them, right? And yes, you guys are all close to the right answer, but I want somebody to articulate it in crisp language, in a logically, completely defensible way. How would you say it?
The function for the football team would be different with the function for the pilots. They're not
these are two different stories.
same.
They're two different stories, but the same thing happened. Shouting led to better performance.
I think
Chandar has
go
Chandar
ahead.
has written it down in the chat for everyone. I'll just read it.
Okay, yes.
It was an example of regression towards the mean.
Absolutely right. I just taught you regression towards the mean. So let me explain that. It's an example of regression towards the mean and another concept that I'm going to explain. So how do you see, guys, regression towards the mean is one of the most non-intuitive things that we know. In a great statistician, Stigler, wrote a book. I believe it's called the 6 pillars of statistics, or 5 pillars, or I've forgotten how many pillars. But one of the pillars is regression towards the mean. And human mind has a very tough time understanding that. See, what happens is, imagine that you have some pilots who did badly, right? Who did horribly bad. They did horribly bad for a whole variety of reasons. The guy may have not slept well the previous night, may have drunk a little bit, may just be having, the body may be having aches. The body has its ups and downs. For all you know, his girlfriend had just dumped him that morning, right? Right? Or many things may be happening to the person's life. Or there are so many factors that you don't know about that caused the pilot to have a particularly bad day. And we all have good days and bad days. How often have you woken up and gone to work and realized that today just nothing seems to work? Isn't it? It happens. And then some days you go to work and whatever you touch works, and you suddenly feel that your IQ must have jumped 30 points while you were sleeping. Right? It happens to all of us. We don't know. There's a variability built in, and that is the epsilon. On the days when the variability is hugely negative, you're having a really bad day. You get shouted at, but the next day, the variability may by random chance be in the other direction, right? So whether you were shouted at or not, you don't know, because the next day you would have done better anyway. So if you really want to say that because of the shouting, the performance improved, the right way to do that would have been to break up into a control group. And that's why in medical, we always do a control group, and psychology, in medicine, in economics also nowadays we do that. So you have a control group. Don't shout at a group, divide it randomly. Some people you don't shout at, some people you shout at. Better still, some people you give some positive feedback, some people you talk to at all. Some people you shouted, and next morning you see what you will see generally. And so people have repeated such studies is that they all improve, right? Invariant of whether you said positive things, negative things, or didn't talk to them at all. The extremes are pulled in. It's regression towards the mean. Are we seeing that? But believe it or not, it's very hard for the human mind to grasp. We always associate causation to sequence. But sequentiality in time dimension does not imply causation. All your life in statistics, you must have heard the phrase, correlation is not causation. That is true, we'll come to that. But one of the cardinal mistakes we all make is we think if event B happened after event A, B is likely the cause of A, especially if somebody can make a persuasive argument, right? As in this case, the improvement in performance in those pilots is because they were shouted at, right? Or this football players is because they were shouted at. If you read the newspaper, guys, and I invite you to do that, within a week, you will be able to pull up examples where people have written papers, written articles, where they have mixed sequentiality with causation, whereas what really was happening was regression towards the mean, right? And sequentiality is not causation. See, I came to Silicon Valley in 1999, and there was a dot-com boom, and billionaires were manufactured. I must be the cause, right? Right? So the absurdity of sequentiality is right there. Just because B follows A doesn't mean that A caused B. Are we together? Yeah, go ahead.
What were the outliers, right? Some people may be really good. So those people should be removed from this particular situation. Some people will always perform much better than others. Right? Yeah.
No, they are there. See, there is a baseline value. So they are the high level. Let's say that they perform at 90, but within 90 score out of 100, they will fluctuate between 95, 98 to 80, 85. Everybody has random fluctuations, right? So we all have error bars associated with it. So that is important, guys. So the point is, remember, sequentiality is not causation. Do not infer causation from it. And quite often there are many things are true, right? If you look for that, for example, if you're in the United States, and I'm sure in every democracy, if the economy booms, whoever is the president or the prime minister immediately takes credit for it. If the economy sinks, it was the cumulative effect of the mistakes by his predecessor. Have you seen that? Right. So, right. So this happens every time, right? This is a mistake. So the next thing we will talk about is correlation and causation. Causation means A causes B. Right. Now, without defining what correlation is, and today we'll have a more precise definition of correlation. So the second half will go into statistical concepts rigorously. But at this moment, let's be with stories. Right. So there are many things that happen in life that people ascribe to causation. Even researchers do. Right. So I'll give you some very interesting examples. Suppose, so they found in US, for example, that there was a therapy at one time that was very popular. It was called hormone replacement therapy for women, right? So women have a process called menopause, and if you take hormone replacement therapy, generally you stay perked up, you look younger, you stay younger, you stay more active. It was supposed to be the miracle thing, right? You generally feel good, right? You don't feel old and so forth. And nowadays, of course, there's hormone replacement therapy for men also. Now, when it came out, it was advertised as the miracle thing because they found that people who were taking the hormone replacement, the more stronger dosages they were taking or more regularly they were taking, the better their general heart health. right? So what do you conclude from that? What the researchers concluded is that, yeah, this correlation means that this hormone replacement therapy, in some ways that we don't understand, improves the heart health, the coronary health, right? And it was literally marketed, at least in the Western hemisphere, as the magic thing, right? Makes you younger, makes your heart grow better, and so forth. In the complete absence of any scientific or biological causative discovery, researchers had no way to explain why A caused B, but they felt that A caused B. So I want you to now, with the discussion that we are having, can you argue against it? There is a correlation. There was a correlation based on how regularly you were taking hormone replacement and how your health was, or between people who took hormone replacement at all, women who took hormone replacement and their cardiovascular health versus women who did not and their cardiovascular health. So would it not be fair to give credit? Perhaps credit is due to give credit to the hormone replacement. Anybody would like to agree with that or contest that?
You could try the placebo and see if that works, because the patients knew they were taking something.
That is one way. Have a control group. Very good. But how could you just refute this study on its merit without doing any further experiment?
Maybe because they thought that, they're taking the miracle medication psychologically. They were thinking that something is helping.
Induce the psychosomatic response. There was an induced psychosomatic response. Like, very good, right? And I can see your marketing and advertising background come in here.
Yeah.
Very good. Anyone else would like to hazard a guess?
I just trying to find a link. If you're taking hormone replacement therapy, you feel active for longer. Maybe they're exercising a lot more, and that's improving their heart health.
So you are at with the causative aspect, that it will basically do something that will make your heart better. It will change your lifestyle for that.
Good, you feel good, you are more active.
Yeah. Anyone else? Yeah.
I think the people who took the hormone replacement therapy were already more concerned about their health, so they might have done other things to improve their heart health other than take HRT.
Very good, Andrew. So in other words, you haven't controlled for factors. How about the fact that hormone replacement might have been taken by a biased sample, a sample that began healthier? Andrew, Albert.
So there are the examples of people who are not successful. So only maybe positive results were reported.
No, the study was not, it was not like there was no malicious intent there, right? Anybody else would like to hazard a guess?
I guess everybody loves to sell their logic, actually, even if there is no logic.
Yes. I mean, obviously, this is a great marketing opportunity, and pharma makes huge money from that. But I'm claiming that as a data scientist, see, I'm training you guys to think correctly. Can you refute the argument on its head right away?
Because that was not the end result that they wanted, actually.
Oh, they definitely wanted that end result, get a good cardiovascular. Go ahead.
What was the age group of the women who took it?
By construction, you can imagine that these are women who are entering menopause. When do women enter menopause? I have no idea.
51
51
is the average.
is the average age. Yeah. So guys, I will let you ponder over this question, and I'll give you an explanation in a little bit, but I'll tell you a different story. In US, as you know, a lot of the history of this country has been that the settlers came, and they often, in the South especially, they had huge tobacco plantations. It was big business. The country changed, but tobacco remained big business. I don't know if it is still big, I think it's still big business. So you have tobacco plantation. In fact, that's how, if my understanding is right, that's how a lot of people were brought from Africa and from India and so forth to work on the plantations. So tobacco gradually, as biological and medical sciences advanced, there was a general realization that people who smoke, they also tend to have lung cancer more often. There's more incidence of lung cancer in smokers than in non-smokers. And so in the beginning, there were lawsuits and people trying to get smoking stopped, tobacco banned, and they weren't succeeding because tobacco is a big industry, and they would bring the gazillions of lawyers. And this is a real history of the country. Of the United States, it was hard to win against them. They would always have some. They said the evidence is insufficient. When the evidence is insufficient, it's easy to poke holes in it, and they could easily poke holes in it. But gradually, evidence began to mount. The legitimate scientists in research labs are beginning to see increasing evidence that this is really true. When people smoke a lot, they have a significant incidence of cancer. So what did tobacco do? They said, oh boy, there's evidence mounting against us. So we need to open our own labs. So they opened specialized labs where they hired specialized scientists who did very specialized experiments, whose only conclusion was that smoking is beneficial for health. Right? And no matter how much you smoke, it doesn't cause cancer. There's no data that shows cancer in their labs. And so they would produce counter evidence. But it went on, and gradually the evidence began to mount quite a bit. Then at some point, there was again a lawsuit, and the big tobacco said, this time it's hard. There's too much evidence against us. And there were all these correlation charts showing, look at the correlation, the number of cigarettes that you smoke. In this, the cohort that smokes daily 4 cigarettes a day has this incidence of cancer. Whereas the one that smokes 1 a day has a slightly less, and the one doesn't smoke at all has no or very, very low incidence of cancer. So you have a correlation. So then they had to defend. And so how would you defend? Anyone has an idea? How would you defend?
Yeah, I would say simply the user doesn't know how to smoke. He smoked the wrong way.
Yeah, possibly.
It's as simple. If you're an amateur, you're bound to do the mistake.
Okay, so then you can say that, okay, now it's the responsibility of the tobacco companies to educate users, right? But they didn't do that. What else? How would you argue against it? And the argument is actually beautiful. So at that moment, the big tobacco thought they need to get big guns. So one of the greatest statisticians is a statistician named Fisher. Sir, what Fisher? Okay, I'll remember his name, is escaping my mind, a British. They flew him from England, right? And knighted, I mean, see, when you have sir attached, you're knighted or something like that. You have gotten, the Queen has put some title on you. He flew in, and by the way, if you look into the books, we will learn one of his algorithms. We'll learn quite a few things that he ascribed to this Fisher. He came in and he says, what's the problem? He says, evidence is there, all these correlations, and they seem to show that smoking and tobacco use, and there is oral cancer and there's lung cancer and so forth. He says, no problem. Goes to the code. They say, they bring up the people bring up all these charts. He says, I completely agree with it. And well, if you agree, then we have won, isn't it? The other side has won. He says, no, absolutely not. He says, all you have to do is turn the charts a little bit, rotate it a little bit. And as you can clearly see, smoking causes people to, cancer causes people to smoke. Right? When people have cancer, the way he positioned it is, when people have cancer, they are suffering, right? And cigarette is a great, tobacco helps alleviate that pain, right? Soothes the nerve. So what about the people who, well, don't have cancer? Well, he claimed that they have latent cancer somewhere in the body. They are in pain, and so therefore they gravitate to smoking. And this tobacco is doing great public service. They're, they're taking pain alleviation for a big problem, right? So do you see how a correlation can go either way? Do you see that? From pure correlation, you cannot, and I believe this is a very good thing, because while obviously he had a devious intention, it did bring out one point, that the scientific community was not making a strong argument. Correlations are not enough. Later on, we had more precise understanding of how exactly tobacco leads to cancer. We know the chemical pathway better. You have to create the causative chain scientifically in laboratory, demonstrated, and then you have evidence. Pure correlation is not evidence, because you can actually turn it upside down and argue the other way around, right? So what A may cause B, in this particular case, tobacco may cause cancer, cancer may cause tobacco with equal validity. You can't contradict it. Just because you feel it's not right is not argument enough. It may be true, right? If you notice, a similar argument is being made for weed and for other drugs also, legalizing other drugs today, with different degrees of validity. Weed has been shown to have genuine medical benefits, so it's a slightly different topic. But now I'll go back and ask you guys the other question. But now I'll tell you a story that is even more ridiculous, right? Oh, more case studies. Let's learn through case studies today. In US, there is a big breakfast industry. Most people on earth, when they wake up in the morning, their mom and dad have cooked something nice in the kitchen. In India, it is usually a nice uttapam or idli or dosha or paratha. True, isn't it? In the Western Hemisphere, especially in the United States, at one point, the breakfast industry took over. And so the convention was, you would open this breakfast and out would pop colored loops and all sorts of multicolored, sugar-coated, right? Total starch, horrible things. And they showed, with validity, they showed that people who have a nice, good breakfast, who don't skip breakfast, they tend to be slimmer, right? And have generally better health. So there was a whole belief that, you need to take your breakfast very seriously. Even now, you go to any health site and you'll find some guy or the other advocating this wisdom. You must have seen that. And it is all based on this old study. Now, could you poke holes into this? I'll let you think about how you would poke holes, but I'll end with a really obnoxious example. Obnoxious because I hope you'll remember. This happens to be true. I don't know where I read it, but it's so obnoxious that it's stuck in my mind, right? India and China, they have something interesting correlating them. The population growth curve of India, apparently, I'm told, matches closely the population growth curve of donkeys in China. So unless you feel that activities in India is influencing the donkeys in China or vice versa, how would you explain the correlation? So think about it. Why is there a correlation? Right? Can we therefore conclude that one is influencing the other?
They could be independent.
They could be altogether independent, and yet there's a pretty good correlation. And a final correlation that I'll tell you. If you look at the temperature curve in some city, the sun is shining, it will go up, then clouds will come, it will go down, then maybe rain comes, it goes down even further, then sun again starts shining, it goes up a little bit or whatever. You take temperature, you take humidity, etc. You'll get some stochastic curve, you get some curve. If you look into the stock market, more or less amongst the thousands of stocks, you'll be able to find some company's stock which closely matches that curve for that day. So did the temperature here and what was happening here in your city affect the stock price, or the other way around, or what happened? Why are they so closely looking like the same curve, more or less?
Naturally occurring populations.
No, no,
Or-
stock market is financial market. You see some companies exactly like that.
Yeah, but it's one company amongst 5,000 or 10,000 companies. That error is bound to happen.
Close, yes.
It's basically random, right? That's it.
It's basically random, yeah.
Chance.
Yeah. So yes, good point. So let's draw some lessons from it. Correlation can be pure accidental. I'll call it adventitious correlation. Right?
They're able to go and repeat the experiment for the next day and for
Yeah,
at least the next 100 days or so. And
right.
then they find the same.
Then you wouldn't see that. Unfortunately, that company's stock won't do so well. Right. So this clearly is an example where it is unrelated, isn't it? Right. So now let me, by the way, there was one more story I wanted to give, and I'll leave that as a puzzle and give you a break to think over. And I want you all to discuss amongst yourself and come back with answers. The next story is, suppose you have taken a few people to Las Vegas and you have given them $100 to gamble. Some will win most people will win some, lose some, right? Or maybe give them $1,000. These days with inflation, 100 doesn't mean much, right? So let's say you gave them $1,000 and they played the markets. After a little while, at the end of the day, there will be some winners and some losers. Some people will be big winners and some will be big losers, isn't it? Now, what you do is you take the really big winners because they really seem to know how to win, isn't it? Because they have come back with big things. Next day, you again give them $1,000. What do you expect? So think about that problem, because that's how, by the way, traders are hired. Any trader who does well for a given amount of time immediately becomes a star trader, and all the trading houses want that person. And ponder over what happens to such traders. It's real life. These things happen. So let's take a break. We have been talking now for about the better part of an hour. It's time for a break. I'll give you guys a short break of exactly 10 minutes. Ponder over this, guys. Don't take it passively. Come up with answers. Because if you think about it and ponder over it, then when I explain the theory, because now I'm getting into statistical theory, it will all make sense. So 10 minutes break, guys. All right, guys. So I posed a few puzzles. Let's take the easiest of them. If you take the people who were extraordinarily successful in Las Vegas on a given day, how many of you vote that they really, like, there are people who are either lucky or who have figured out the system. The next day also they'll make money. Any takers for that? Anybody with experience?
Okay, so I know that I I haven't played poker myself, but I know a friend who does, and depending on the game you play at the casino, you might have different chances of winning. Poker is one where skill actually matters, so you have to make sure that the people who won big weren't all playing poker.
Okay, let's take poker out of the equation.
Okay, yeah. So if poker's out, then I'd argue it's pretty much random, and the next day you're likely to see most of them earn less or lose less, or like earn less than they won and also lose less than the people previously also lost.
Yes. So I'll illustrate this with an example, guys. And this is how actually a famous paper did it. Imagine a box. And so now we are getting mathematical. How many of you play a game? When I was a kid, it used to be called the bagatelle. What you would do is imagine a horizontal surface like that, and there would be all sorts of pins or obstructions, right? But judiciously placed. And what you would have is, let me put bins. Obviously, many more pins in here. I have underrepresented the number of pins and lots of bins, right? So what happens is from the top, you drop a ball, a marble. Now the marble will go and hit the first one. It goes and hits, and after, or it will hit something, right? Once it hits this, it will, gravity is pulling it down. It may go this way, it may go this way, right? Then it will hit something here, which may cause it to go this way or this way, let's say, right? And it may have gone here, it may have gone. So you're pouring it, it's randomly falling at whichever direction it is. At the end of it, what will happen is the most high, so you will see interesting, if I were to just exaggerate the marbles that have accumulated here, when you drop a lot of marbles, would you agree that it makes common sense that in the center would be most marbles? Because there's no reason why they should be more on the left or more on the right, isn't it? That random chance will keep pushing them to a distribution like that. Does it make sense? Right? So now take the same game and let us say the winners, you impose a game on it. You say the people who are here are winners. These marbles are winners. These guys are losers. And once again, you have a second round to this game. You pour these things through a funnel into yet another set of marbles. Sorry, pinheads. And here are your pins here. These marbles that are there as an outlier, when they come and start falling here, do you expect them to all accumulate in this region X? Or do you expect to again see a uniform distribution, sort of a bell curve distribution?
Bell curve.
Normal says that, because there's no reason why you pour this, you replicate the same situation above and below, and you should see different results. So what has happened? Think about what has happened to these marbles. Their location has regressed. Most of them have regressed towards the mean, isn't it? From being outliers, they have been pushed inside, and anywhere in, sometimes severely inwards, they have become losers. Does it make sense, guys? Just do this thought experiment. And there's a lovely word in a research paper that it was called. That is one of your readings. So Kyle, we need to release the second paper for reading, a famous research paper. So a great mathematician showed this just with this simple example. Now, there's more to it. The fact that it's a bell curve, we expect it, but why it is, we'll come to that later. What it shows, regression towards the mean is very obviously there. Now, what is the causative? Because in this case, the causative factor is practically zero, right? It's just like, now, when you send a bunch of random people to play games in a casino, most of them will win some, lose some. They are like this. Occasionally, if they win, they move to the right. If they lose, they move to the left. They have 50-50 chance, but actually not 50-50 because house has a leak. It keeps taking some money out of the system. That's how the house wins eventually. But you do that. So most people would have lost some, won some. Some people would have lost a lot and won a lot. But if you make them repeat the next day, they are not going to be winners. And do you see how you can demonstrate this? Right? This is a fact, by the way. Have you ever walked into a bank that will show you the investment schemes, the investment funds? Walk into any bank here in California, at least, and say, I want to invest money. And all of a sudden, they'll become your best friends. And they'll show you all these wonderful portfolios on how well they have managed money, these many money managers. And they'll show you that from this period to this period, this particular fund did very well. It had 20% growth, it had 15% growth, and so on and so forth. But then you come out feeling that you don't know much about money, but these guys live and breathe and think financial strategy. So is it a good idea to give them your money? Most people do, by the way.
No.
Yeah, why not?
Because just like historical evidence shows you should do it, but they cannot do it for long. It's just one good year.
You know, if you do enough stocks, you can always find a collection of them or
Yeah.
some little fund which has done well for a short period of time. Right? Generally, you base some heuristics that, oh, the tech will do better. So you just go create a bundle of them. And for a while, it begins to look that these guys are geniuses, right? But actually, that is exactly this situation. Next time around, the next few years, everybody is puzzled. I don't know why my fund is not doing so well, right? But while it's not doing so well as promised, the fund managers are always getting their 1%, 2%, 3% of your portfolio, whether your stock goes up or down. Have you seen that? You keep losing money. So I call it the mathematical idiocy tax. If you are mathematically illiterate, these guys will take your money one way or the other. Why? Because there is no the financial markets are extraordinarily efficient. I think, Hari, you made that point. They're extraordinarily efficient, right? And as being extraordinarily efficient, unless you have an unfair advantage, you have powerful machines to do high frequency trading, or you have inside information, there is no way, fair way, that you can beat the indices, beat that. In fact, there is an experiment done. It's called the random darts monkey experiment. The thought experiment is that a monkey throws darts onto a board with lots of stocks written. I don't know if they physically get a monkey to do it or it's just figurative, but randomly you pick a stock and you follow.
No, they actually made the monkey to pick the stocks.
Oh, they actually made
and it beat the market continuously.
Beats the market continuously. Exactly. So what happens is that because it's random, it's actually closer to the index funds, the Dow Jones Industrial Average or NASDAQ or something, much more likely to be closer. Whereas these money managers are human beings who all have biases based on experience. Their experience said that they ended up in this area winners because they have certain theories that will lead to their winning. Time and time again, they fail, right? In fact, no one has ever beaten that random darts from monkey experiment. No one has beaten that, right? You can do this experiment. Take kids, put their finger on random stocks, good or bad. You just take it, create an index out of it, sufficiently many, follow the index, and you see if all of this snake oil salesmanship that these banks do has any merit in it or not, right? So something to learn from that, guys, which is that this is an illustration of what? This is the clearest illustration of regression towards the mean. Remember, here I said that y is equal to fx, the causative factor plus epsilon. In this particular experiment, the causative factor is practically missing, right? The people who won in casino, they all won because of the epsilon factor. It is all random, not causative. But if you talk to them, they say, I use this and that strategy and there was a cause to it, right? So if you know that it is random, you know that they will regress towards the mean, right? This is it. Now, let's go back and ask this correlation thing. We realize that if the day's temperature can easily have a correlation with some stock, is adventitious. There is no head and tail to it. You shouldn't read into it, right? But then there's the other extreme where perhaps there is a relationship and you need to study more. For example, if you look at, you put a kettle of water on the fire and you keep measuring the temperature of the water and the amount of time that has passed, you will find a fairly strong correlation between temperature and time that has passed, the time that the kettle has been on the fire. Would that be reasonable? That if you look at the temperature of the water and with certain margin of error, this is the time on fire for the kettle, and this is the temperature. you would find, would you be convinced that the results would be like this? And after that, it plateaus off because water beyond boiling point won't go up. But at least in the beginning, you do see a positive correlation. So not all correlations are adventitious. The other extreme is a correlation may indicate a causation. Now, if you think about the causation, more temperature can't cause you to put kettle on the fire. Temperature is the effect, not a cause. The only thing that you can control is how long you keep the kettle on the fire. So your inclination should be to find out if putting more kettles on the fire, you see the temperatures increase, and you can put control experiments, put some kettle in the refrigerator, put some kettle on the normal place. And with time, you see their temperature doesn't rise, but on a fire, it does tend to rise, right? So then you can start going deeper, and soon you will discover that there is a rich and beautiful theory of thermodynamics and statistical mechanics and physics, right? So there is real causative. See, so I'll write this: correlation may imply, may indicate, and this is the operative word, possible causation. It does not prove causation. It may indicate possible causation, right? So these are two extremes. They're completely random, adventitious, or there is some possible underlying causation. The underlying causation is, of course, the heat energy. The fire contains heat. That heat is transmitted to the water temperature rises, right? Now, there is a third case, which I came to, which, what other stories did I tell about correlation? Oh, the donkey population. It turns out that the Chinese donkey population, donkeys tend to pay particular attention to how Indian population is growing. Why would that be? Right? So that is when, now go ahead.
I don't know, I could be wrong. They're both naturally occurring populations without any population control on them. So it's normally.
But the tiger population in India has been decreasing. Human population is increasing, but our tiger population is decreasing. Our elephant population is decreasing. The pandas in China are decreasing. So you can't argue that because of natural expansion, the population should be increasing.
I don't think you can compare tigers and pandas with donkeys, right? Donkeys are used, they are bred to carry the burden. So if the economy increases, they need to have some.
You're close. You're getting to it. Yes, that's a very good way.
There is a need for that. So that's why they are bred like that.
Why are they correlated?
Just random. I don't think there is a correlation.
Wait,
go ahead.
Does China breed donkeys to ship to India?
No, it doesn't.
Okay.
The mystery deepens. Okay. So see, guys, I'll give you an explanation of what it is. Sometimes both of these are effects of an underlying latent cause.
Latent cause.
A latent cause is causing both of these to happen in two different scenarios. So I'll give you a possible plausible explanation. See if it rings with you. Both India and China were British colonies. Under British colonies, they were practically plundered, and when both these countries became free in the 1945 and 47 respectively, they were, to put it blandly, land of starving beggars. I've seen that. My grandparents have seen that poverty, and I have seen poverty. I come from one of the poorest parts of India. I've seen unbearable poverty, right? People who are skeletons around me in my own family. So India and China both had to rebuild a country which was in countries which were in shambles, where there was famine, there was starvation. And from there, they had, once they are freed of colonialism, they rebuilt these countries. Each country is the government, whatever we may say, and we may criticize the governments, they have done an exceptionally good job in both these countries after in the post-colonial world to bring their population up. Today, if you go to India, and I can say that I go to India often, when I go to railway stations, I don't see a sea of beggars that I have to walk in the midst of to cross from one platform to another. I don't see lots of beggars sleeping on the platform. I don't see lots of beggars sleeping on the road. Generally, I find well-fed people, right? They may not have the fanciest cars. They may not be having the latest iPhone Pro, but they are people who are, broadly speaking, not starving. Same is true for China. They have done. So it is when natural resources, when are available, when food is available in both these countries, what happens is everything is well fed. We get well fed as human beings. Our dogs get well fed, our donkeys get well fed, our cows get well fed, right? All of them get well fed, isn't it? Even our cats and dogs, I mean, wild animals who steal our food get well fed, isn't it? And so when there are natural resources, the standard Malthus dynamics, what do you expect? Population to grow. Population grows when natural resources are available. And so the population of India, it is no surprise, is correlated with not only the population of China, but you can pick any animal in India, any domesticated animal, and so on and so forth. You would probably see the correlation. So what is the correlation here? What is the causation here? It is the way these countries have managed to essentially rise from the ashes, right? And they have had very parallel trajectories of economic growth, which is responsible for this, right? So that is the third way of looking at correlation. So that is the in-between part when correlation has a latent or underlying cause, right? So this is number one, adventitious. This is, it is, one is actually causing the other. This is number three. Something else is causing both of this, isn't it? And there is a number four also. Now let's go back to our lovely American breakfast of Fruit Loops, right? And sugared whatever wheat and whatever that are marketed as healthy dishes. And if you pick up any cereal box in America, they will say healthy, American Health Association, and there's a big heart symbol saying how it will improve your heart, right? I don't know if you have seen that. I actually picked up a cereal box at home and noticed that it was true. It was there. Why do you think that is true? Do you think really that those Fruit Loops and those sugary starch, sugary carbs are beneficial for your health? They'll make you lose weight and get healthier. What is going on? Why is there a correlation there?
No, but I think since to eat breakfast, you have to get up early in the morning. And if you get up early in the morning, then it makes a sense on your health because you will be doing some exercise or something. Yeah.
Yes, partly, maybe. Anything else people can come up with?
Well, it may depend whom you fed. If you fed really, really hungry people, then of course their health will improve. What is a starting point? If you fed really healthy people, maybe it won't affect so much. Maybe they will go overboard and gain
I'll
weight.
give you a clue, Raj.
Yeah.
We see in our own neighborhood, since you and I live in the same neighborhood, a lot of homeless people. Do you think they wake up in the morning and have those lovely Fruit Loops with milk?
Probably not.
Probably not. What about the janitor, the people, the actual salt of the earth, the people who are actually keeping this world going? Your mechanic, your driver, your janitor, your gardener, your construction worker. Do you think they actually live here in Silicon Valley or can afford to?
No,
They all commute.
definitely, yeah.
They commute long distances to come here. When do you think they leave home to be here at work?
Yeah, early.
Very, very early in the morning. Do you think that these poor people who are really the salt of the earth, the real hardworking people, get any chance whatsoever to have breakfast, a decent breakfast? No? They grab what they can and they run to get into their car and start, or their commuting vehicles, commutes and trains, and start coming to work, right? There is the confounding factor is people who are poorer, who cannot in this country, at least, afford good nutrition. You probably know that people, you go further from the city, you end up with what are called food deserts. You literally find no good grocery store with healthy food there. All you find are the 7-Elevens and the, overpriced places where it is not food, it is processed junk that they live on, right? Who by and large can afford all of these expensive cereals? The well-off, reasonably well-off, right? Who have time, who have leisure, who come home after the 20-minute commute and go for a walk or a jog, or like you and me, Raj, take our dog for a walk, right? So what do you expect? This is also the population that, I mean, it buys those fruit cereals and whatever, because it's affordable, it's available in the groceries and we can afford it. So therefore, the confounding factor is that we are healthier than the people who work very hard, barely get good food at all. We are generally healthier. And these cereals, this junk, sugary, starchy junk, is a factor that is actually screwing our health, not improving it, as common sense would tell any scientist, isn't it? But nonetheless, it manifests itself as though there's a correlation between having that and health, right? That the people, so the observed data was that people who have good breakfast tend to be healthier, slimmer, right? But they just happen to be more affluent people. They are not people who are, just struggling to keep alive, commuting long distances and working hard. They are not the people who are, living in the bushes behind your house. And that's the difference. Using the same argument now, explain what happened to that hormone replacement therapy. Why is it that there's observed data that people who are taking hormone replacement tend to have healthier hearts?
They're well off. They're well off.
It's a discretionary, it's an optional procedure, right? Most health insurances won't cover it, right? Or you have to buy a pretty good insurance to get coverage for it in the United States. HRT is the privilege of the settled people, well-off people. You don't have a health insurance or you have a crappy health insurance, go try trying to get a hormone therapy. You won't get it, right?
But being, well off, does it mean their heart is also healthy? Or
No,
does that?
yeah, it does. See, what has happened is, no, it doesn't. But the paradoxical thing is, there are more well-off people amongst the healthier, because in this country, you need leisure to exercise, even if you want to. The poor people, unfortunately, have no leisure. They wake up in the morning, start commuting. By the time they come home, they're totally tired. They have to sit and help the kids with the homework, cook dinner, whatever they can, or get whatever food they can, and they sleep. There is no leisure. So where's the time to improve your health? Other thing is, the food they eat is hardly food. It is processed, very low grade, very unhealthy food, because that's all they can afford. Try going to McDonald's every day in America. In India, I know McDonald's is a prestige thing. You dress up well and wear a tie and go to McDonald's.
I think in India it's kind of reversed.
It's reversed now, is it?
Yeah. I mean, if you're only wealthy, then you go have junk food. So
Oh yeah, that is right. That's what I'm saying.
Yeah.
Yeah, you wear a tie and be healthy. Wear fancy clothes, designer clothes, and go designer jeans and go to McDonald's or court and so forth. In the US, is the reverse. The healthy people go to Whole Food, right, and buy organic, locally grown food, right? The unhealthy, the rest of us go to whatever grocery we can find, whatever food we can find. And America is notorious for the so-called food deserts. Vast tracts of America actually has no healthy food at all available. There's no grocery store at all. So they live on junk food. McDonald's are everywhere. And I don't want to single out McDonald's. All of these, Taco Bell, or whatever it is. Yeah. Breakfast burritos and this and that are everywhere. You go to 7-Eleven, you'll get a preservative-ridden, some junk or sugary junk, Slurpees. And people need energy to just go to work. They don't realize that those are just empty calories. They all have vitamin deficiencies. They have severe deficiencies. There are people, America is the land where homelessness is at an epidemic level at this moment. There's a huge disparity between the rich and the poor. So in other words, well, we're not talking about American system here. Unfortunately, I tend to be on the, people call me left wing. So I shouldn't speak much. Confounding factors are there. Whenever you hear a study like that, that doesn't make common sense, like fruit, good breakfast is better, will slim you down. And by the way, breakfast in America is just Fruit Loops, right? Or there's junk cereals. Take it with a huge grain of skepticism. Ask, what are the confounding factors?
They say balanced breakfast.
Yes.
They don't think healthy.
Yeah.
They think
Balanced breakfast. Of course. Now, that's a great legal save, right? Because the balance means you also take a banana with it. Yeah. Yeah. So now for the hormone replacement therapy, the same argument applies, and people have studied, though, by the way. They found that this was true. The people who were taking hormone replacement generally were healthier, right? Well-off people. And so, of course, their heart was in. So the causation was the other way around. Do you see that? There is a causation. Being healthy, well-off is more likely to cause you to go take hormone replacement therapy. Do you see that, guys? Huh? Right? Well, it turned out later on that it actually increases your chances of cancer. So I think hormone replacement therapy is more or less phased out.
Yeah, especially in Marin County.
Marin County.
Saw that breast cancer rates skyrocketed because they were all able to afford the hormone
replacement.
therapy.
Yes.
They had a concrete population that they could prove it
Yes.
had this unfortunate effect.
Yes. So Kate is mentioning the story. For the rest of your remote, I'll mention. There is a county here called the Marin County. It is like, it's the destination. You have made it in life when you live in Marin County. And if you don't live in Marin County, you have ways to go, right? So those people are all well off, very rich, very well settled. And it turned out that they had a pretty high usage of hormone replacement therapy. And there was a very high incidence of breast cancer. Almost it became the epicenter of cancer in the Bay Area. A lot of research has been done. And now, of course, HRT is in disrepute. You don't do that unless you absolutely need it, right? So anyway, guys, these are stories to bring home certain points. The hardest lesson, the lesson, these are hard lessons, guys. These are simple. In the data science, you will learn a lot of things, very sophisticated things. But I wanted to take some time out to get you a grounding in statistics. Some of the greatest people in this field, data scientists like Stigler, have pointed out that the human mind seems incapable of grasping it. When you explain it like that, they will all say yes, yes. But after a little while, we'll all go and make the same mistakes. So if you want to help yourself, instill into your mind that regression towards the mean often explains many things to which people give a causative explanation. Also, correlation is not causation. We know that. That's a cliche. But then there are gradations to it, right? So for example, if a guy says, I really studied hard and my grades came out, I got an A grade. You cannot say that correlation is not causation. Just because you studied and the likes of you studied doesn't mean it was not the reason you got A grade. It may be the reason. Sometimes there may be a possible causation. Causations express as correlation. but correlation does not prove causation. That's the way to do that. Then there may be an underlying cause that's causing it, both of these things, correlations to happen, or there may be confounding factors. Confounding factors are so prevalent. Most studies that you hear about health and nutrition, consider it with a pillar of salt, generally, right? As you will, just take the studies of 5 years ago and the study of today, and one would contradict the other. They would go in opposite directions. It's a fact quite often, right? So not always, I mean, you can't disparage your entire field, but a lot of it. Why? Because it's very hard. Human beings are complex. There are a lot of confounding factors, and it's hard to account for all the confounding factors. So all of that being there, now we will get down to brass tacks. It's 9 o'clock. Today, I plan to have an extended session, guys. Are we all willing to go a little bit more till 10:30? Half an hour more?
I'm okay.
Okay. All right, guys. So we have reached a place at which we'll bring it down to statistics. So suppose you have some data. So we will use notation now. Let me just call it super fast, or let's use some funny words. Hypersonic flight over the statistical land. Right? Imagine that you are, well, the hypersonics are not yet there. Let's say supersonic. You are in, what was that airplane called that did supersonic flight from here to London?
It was the Concorde, I think.
Concorde. Concorde. So we are on a Concorde, and we are flying over the statistical land, right? Obviously, you can only get a very, very high level view of what it is. So in this view, but we'll still grasp a lot if you sort of pay attention. Let's just say that there is data. So I'll use this symbol always for data. It is conventional to use this symbol. D. This do you notice this fancy scripted D? Scripted or calligraphic D. This is quite common. Many textbooks use this, and I will follow this convention. D is for data set. What is a data set? A data set is a collection of datum, data instances. Are we together? Let's take some simple data, for example. Consider in practical terms, height of a sample of people. Now, I use the word sample. What does sample mean? Whenever you use the word sample, you're acknowledging that you're not looking at the height of all the people in the world. That's somewhat impractical, right? So if you take a measuring stick and go around the world measuring people's heights, you won't succeed. While you are still measuring the heights, some people will die, some new ones will be born, and in some dangerous places you might get killed, right? So anyway, I'm making it a fun, but the point is it's never practical. So, not ever. Quite often, it's not practical. Quite often, it is not practical to measure an entire population, right? When you cannot do that, you really can't do that easily. Sometimes it's just not possible to begin with, right? So, for example, if I ask you that let's say that you have a certain topography, right? And I ask you how much iron is there in the different rocks in this region. What is the average amount of iron, right? Or what's the iron for every square meter or cubic meter of rock or so forth. It's not practical to basically dig up all the rocks, pass it through your scientific instrument, measure the iron, and then somehow restore the rocks you have destroyed. You can't till the whole earth. So it is not. You essentially have to practically take some samples, right? So samples are subsets of the population. So now samples are subsets. We understand subsets. They are parts of the, in simple language, they are parts of the population. Once you take the parts of the population, now you go measure. So you happen to pick, let's say, take a population. You took about 30 students, 30 people. You measured their heights. Can you draw some conclusion about the human, the entire human population? What is the risk here?
The sample
Too
won't
low
be
of a sample
representative.
size.
So it's a different, all said more is the right answer. But say that again, please. Yeah. And Hari?
I am saying that the size was too low.
So what is right size? You have 7.5 billion human beings on Earth. What would be the right size, sample size?
To be true, it should be basically the representation of the whole 7.5 people coming down to, let's say, how I to say, with heterogeneous and every subset of every kind of guy. How many types of subsets you can make?
Yeah. You're getting into this whole thing of how to sample in such a way that the sample is representative of the whole.
Yeah.
So it's a good, that is a question. So that speaks to an important topic, bias in samples. Bias in a sample is when the sample is not representative of the whole population. Why does it happen? For example, if you are not careful, it happens all the time. You're looking for people, you might just pick colleagues in your office, measure their heights, and come to the conclusion that most people are, their heights are between 5.5, 5 feet 3 inches to, well, if you're in software, you don't often get very tall people, but broadly speaking, 6 foot 3 inches or something like that, right? You might miss the fact that there are children in the world who are tiny tots, isn't it? So you got wrong even the range of values. So bias is there in the sample. How do you create representative samples? And there are a lot of theories or methods of creating stratified sampling. You go to every, you know that people are divided by race. Certain races are tall, certain are not. You go measure by race. Then you get into complication because then comes anthropologists who tell race is a mythical and literally a racist concept. It has no scientific basis. So then you scratch your head and say, what do I do now? So you go to different geographical regions and start measuring, taking some people from there, right? You can try different things, stratified sampling you can do, but it's still very hard. But even if you could go, I'm going to make a statement, even if you could get a truly unbiased sample, your results will still can be wrong, and in fact are guaranteed to be wrong for certain key statistics. So think of the statistics that you learned about. So given a sample made up of elements, let's say x1, x2, xn, all of whom take, so you often call them random variable, like x is a random variable, height, for example. In the language of statistics, you would say height is a random variable. It can take various values, right? So you take certain values, you go get a sample. What are the, if I ask you to describe the sample, you cannot go on enumerating that one guy was this tall, another guy was this tall, and another guy was this tall. People will get bored. They say, okay, so what have you learned? when we try to extract the essence of the data, we tend to use something, a language. We create something called a statistic. A statistic is a measurable, a quantifiable or quantified way to describe the sample data. The data, I'll just use the word data. Are we together? So what are the examples of statistics? One statistic could be range, min, max. See, what is the shortest person? That is a statistic, singular. Max is another statistic. Range is another statistic from here to there, isn't it? So each one of them conveys some information, but the more statistic you gather, it becomes descriptive statistics of the data. So now you notice that it is a plural, and now you know why you end the word with the S. Statistics means there are many different statistics that you put together to get a sense of the data in a quantitative manner. Then we are familiar with some. If you're not, tell me. Mean/average, people often use. There's subtleties involved here, but actually let me avoid the word average here. Let me keep it mean. And mode is the most common. Median, if you sort all the values, the middle value, median. You may remember something called standard deviation. So let's go through each of the statistics and see if we understand what it means. What would the min be? Like, suppose I give you the height as 3, 7, 9, 11, 4, 2, 8. Let's say that this is your data set. D is this. Can we tell what the min is? What is the min statistic? Please speak up, guys, remote.
2.
2 is the min. Now, what is the max?
11.
11. What is the range?
2 to 11.
2 to 11, isn't it? What is the median? And let me throw in, just for good measure, one more number, 3, 7, and sneak in a 7 at the end also. What is the median?
7.
So if you put these numbers in a row, 2, 3, whatever it is, 4, 7, 7, 7, 8, 9. So the middle guy looks to be somewhere here, right? This is your middle. So let's say median 7. What about mode? What is mode?
7.
7.
Sorry, 3 times it got repeated.
So it got repeated 3 times. So this is the mode. This is it. Now, what is the average? What is the mean? Mean is you add up all of these numbers, summation of xi over whatever number it is, right? Average. So now, what is the standard deviation? Standard deviation is represented by sigma. It is equal to x. So mean is represented by mu. So you notice that once again we are following the convention that observables are Roman letters, like xi, the measurements of height. How many samples, how many points are there? Cardinality of your data set is a number, n. But mu, you can't go and pick mu off the table, mean off the table. It's a derived quantity, isn't it? So we use Greek letters for it. Mu and sigma. Mu is the mean. Sigma is defined as, if you remember, what is it defined as, guys? Is this fair?
Yeah.
Right. Sigma squared is this, right? The standard, this is called variance. Variance is People in machine learning tend to use the word variance more than standard deviation. Variance is square of standard deviation. Right? Standard deviation. So each of these is a statistic, and they all help describe the data set, isn't it? Now, there is more to it. It turns out that there is a concept in, we can generalize beyond mean and variance to go to the next level, which is the concept of moments. But before I do that, I will talk about something. So suppose data, there is one thing, it's called the Z value or standardization or normalization. People offer the standardization, normalization, depending upon who you talk to, they'll use these words interchangeably, and sometimes they'll say one is different from the other, but I will call it Z value, is defined as Xi minus mu over sigma. Now, what in the world it is? Let's look at this. Let's Xi. Let's do that. What is the mean? By the way, could one of you please quickly calculate the mean? From this 7, 3, 10, 17, 26, 37, 41, 41, 43, 51, 58. 58, 1, 2, 3, 4, 5, 6, 7, 8, 9. 58 divided by 9.
6.4.
6.4. So guys, when I subtract from the value, a value 6.4, what am I, the mean, what am I telling? How far above or below the mean it is, isn't it? This. And when I scale it with the sigma, sigma is a measure of how spread out the data is. That is why it's called standard of variance, how spread out the values are. Like if you have values that are spread out here like this, imagine a data set like this versus a data set which is like this, right? All the individual elements are tightly knit. You say low variance, high variance, or high standard deviation. Are we together, guys? Because data is literally spread out. The same data is, so for example, if it was not 7, but 7 million or things like that, then the range of the data is large, right? And the spread is large, and spread of the core part of the data is a measure of variance, very hand-wavingly. So if you scale the data by variance, you're pulling everything down to essentially a similar scale. And then if you look at only how far above or below the average it is, you get something called the Z value. So we learned of standardization of data. This is an important concept. Standardization is standard or normal, etc. I won't use the word. Z I is equal to Xi minus mu over sigma. Now, one of the things we do, you'll realize that machine learning, it is never a good idea to work with raw data. Very, very often, I mean, you have to at least consider, should I standardize the data? You can't ignore it. Maybe you don't, maybe it doesn't require it, but it has to be a conscious choice, right? You have to think about it. It is like you wake up in the morning and you brush your teeth. A data scientist sees the data, and first thing, brushing the teeth is equivalent to standardizing the data. Are we together, guys? So go ahead.
So the ZI is a list of elements.
Exactly. So it will as many elements as there are the sample size. So each value is replaced by its Z value.
But then you might have duplicates.
Oh yeah, perfectly. Like 777, all the 3 sevens will become the same Z value, whatever it is.
So you eliminate those values? Or?
No, you keep them. All you're doing is, so let me illustrate this, guys. When I do X1, X2, Xn, we are not changing the cardinality of the data set. We are just creating a de-normalized, let's say standardized, which every value, Z1, Z2, all of them are replaced. You create another data set, which is the standardized version of this, comprised of the Z's. Are we together? So that is an important step. Once you do that, it turns out that now we will talk about something called the expectation value. Expectation value of a variable is a little bit sophisticated thing, but I will today keep it for you. I will deliberately slightly simplify it. I can give you the more formal definition. The more formal definition would involve bringing in this probability, right? So let me give you a formal aside, but ignore it for the time being. Probability distribution. So what is the probability for a value xi to be possible? Right? So you see a value xi, you see a guy who is 7'4". He's very unlikely to be that, isn't it? The probability that human beings are that tall is relatively low compared to 5'8" for men and 5'6" for women, right? So there is a probability associated with it. So if you take a number and you subtract the mean just to see how far it is, deviation from this mean, and then you multiply it by the probability of a xi, right? So I will remove the I because it is generally like it's a continuous variable, dx. In the case of continuous variable, this is defined as the expectation value of x, right? And sort of the this is the expectation value, right? This is the mean value of this number. But we will ignore this. And for the time being, forget about the P's and so on and so forth. So what we will do is, and by the way, this E is written with a double E typically. It's called the expectation value of X, right? X being the height of people. So expectation value is very intuitively the mu, right? If you take off intuitively the E of X.
As if one error you have done, you have put a minus mu. It shouldn't be inside the integral.
This integral, yeah, the mu will come out of its own. No?
The mu is the it's the expected value. Your xpx integral is the.
Oh, yes, you're right. Absolutely correct. Yes, xpx. That will, so intuitively, when you're just looking at xpx, this will become the mean. It will resolve to the mean. But now let us define another concept, which I will call standardized moment. Chandra, thanks for pointing that out. Dized moment. So for that, we will create another concept called standardized mean. What is the standardized mean, or the moment about the mean? It is called the moment about the mean. So now that we have mu, what you can do is, this is defined as something very interesting. It is moments about the mean of degree k. Okay. Mu k, I don't know, we can make it a subscript or superscript. It is the expectation value of x minus mu to the power k. By the way, expectation value, you often put in square bracket, guys. Huh? The E with the square bracket. This is part of the language. Let me just emphasize this. You will often find this notation and a square bracket. What it means is that go find the average of this thing, the squares. Or the kth power, not squares, the kth power, right? Now, you can work out what it will mean for k is equal to 1, k is equal to 2. You can convince yourself that the moment about the mean for degree 1 would be, when k is equal to 1, what would it be? For k, so for example, for k is equal to 1, what will it be? Mu 1 would be expectation value of x minus mu. And that will be expectation value of, it turns out, expectation value of x minus expectation value of mu, which is mu, because mu doesn't change. And this is mu. And so what will it be? 0, right? So moment about the mean, the first moment is 0, right? Now you can do the second moment, the third moment, and so on and so forth. So now comes.
So sorry, Asif. What is a moment again? I didn't grasp it properly.
Moment is defined as this
Yeah,
mathematical.
but what is it? I mean,
So, yeah, I'm coming to the intuition. That's the whole part.
yeah.
First, we come up with some very abstract thing, and you scratch your head, and what are these guys up to? Why are they creating this weird expressions? So we'll see that in a moment, right? See, in reality, it works backward. People have intuition, and from there, they abstract out some mathematics. But we'll start here in the interest of time with the thing. Likewise, in a way, the standard, the kth degree, I will say, sigma of the kth degree is given by some expression. And by the way, if you, the same thing in continuous variable, if you want to write minus infinity to infinity, x minus mu k, right? Dx. Right. This is the continuous, and ignore the infinite part of it. But you can see that this is essentially it. If x has a certain probability and so on and so forth associated with it, you can ignore it. This is the expectation value of x minus mu. Let's say, I would say square this to the, okay, how should I write it? This to the power 2, it is the square root, okay, weird thing, square root to the power k, weird. Take this square, go to the power k. So we are going to now say that the real moment, and now comes this weird expression, the actual kth degree moment, for which I wish I'll notice the big tilde on top of it. And this is sort of the literature people often use. The kth moment, standardized moment, is defined as the ratio of the kth moment about the mean, standardized moment about the mean, and the standard deviation around the mean of the kth order, sigma k, right? This is what it comes to. So let us see what it means in real life. For k is equal to 1, you know that the numerator, what will happen? You are looking at expectation value of x minus mu, right? Itself divided by this whole square root business to the power 1. Expectation value of x minus mu square to the power 1. It doesn't matter because this will go to 0, right? So what is the answer? 0. Do you agree? Because why is this? Because we just convinced ourselves this is 0. E, this is the same as E, x minus mu, and this is mu. So mu minus mu is equal to 0. So denominator doesn't matter. It goes to 0. Isn't it? So it's a first standardized moment of the data, therefore, would be this. What about k is equal to 2? Do you want to play that out and see what happens? It is, let's again plug it into the equation, x minus mu square, right? Expectation value. And bottom is what? Square root of expectation value, x minus mu square, and to the power square. So this square will kill out the square root, right? And this will be equal to 1 because numerator and denominator are the same, isn't it? Right? So you say that the standardized moment, the second degree moment of the data will be like that. Things get interesting when you go to the third and the fourth degree. And that answers your question, Raj. What in the world is this whole business? And why do we consider this weird mathematical concept seriously? So let's see what happens with the third degree. You have expectation value of x minus mu square, cube, right? Remember, third power, divided by, what in the world are we dividing it by? Expectation value of x minus mu square, square root to the power 3, right? And you can convince yourself that this is what is this? What is the expectation value of x minus mu? This is sigma, isn't it? The standard deviation. right? So basically you're putting the standard deviation here. So you're saying standard deviation cube, expectation value of x minus mu cube over sigma cube, which is the same as expectation value of x minus mu over sigma cube. And do you notice that our z came in? Z value came in, right? It is, so what we are basically saying in simpler terms is, it is nothing but expectation value of z cube of the data, standardized values cubed of the data, right? That is the third moment. This actually has an interpretation. It is called the skewness. It measures the skewness in the data.
Asif, don't you think there is an n missing?
No, there is no n missing. Expectation value by definition is 1 over n, right? This is expectation value of, see, what is the expectation value of this? x1 minus mu square.
No. When you convert it into that sigma cube, I thought there is an n missing.
No, that's what I'm explaining why it is not missing. So you have xn minus mu square. The n of these, right? And you divide it by, when you do the expectation value, you divide it by 1 over n, right? This is your expectation value or average in a simple common sense term, right? So there's already a 1 over n factor built in. And this is by definition sigma. This is how you define literally sigma square as. Right? If you look, I mean, square root of this, a square root of this, which is this term here, is, and then it will be sigma. Right, so this is it. So what we are saying is the third order. Now you can generalize from this to the fourth order, right? K is equal to 4. I won't go through the rest of the derivation. You know that this would be expectation value of x minus mu over sigma to the fourth power, right? Or simple terms are big E, z to the fourth power. So you see the elegance. If you use z as your notation, right? You're just looking at powers of z. The standardized moments are powers of z, right?
So that is why you got the z.
Z, that's
You add the
standardized.
z and you just power it. You can.
Yes, you get
the
the,
whole set.
yeah, and its expectation values are the moments, the standardized moments. Now, say that again. Okay. It turns out there is a meaning to this one also, kurtosis. And what kurtosis, so I'll explain to you what skew and kurtosis are. What do they measure? The second moment and the third moment, what do they measure? Right? The interpretation is actually quite obvious once you see it. So sometimes data shows itself as, let's say, look at the 3 data sets along x-axis. One data rises up and is like this, right? Another data is like this. And another data is like this. A, B, C. What can you, how does B differ from A and C?
B is normal. It's not
Normal.
This is symmetric.
symmetric.
You don't know whether it is normal. There are many curves that look like this that are symmetrical. Right? By the way, it's one of the fallacies to believe that every symmetric distribution is normal. It isn't actually. It could be log normal. It could be a Laplacian. It could be, there's a whole family. It could be a beta function. There's a whole family of transcendental and exponential functions, which can all mimic a symmetric distribution. Right? So never just assume it's a bell curve. In fact, there is a very great math professor who has written a classic paper, lovely reading. He asked the question, are normal distributions normal? The reason bell curve is considered normal is because we find it everywhere. Heights are normally distributed, etc., etc. And generally you ascribe something called a center limit theorem, which I'll explain right now, as the causation why bell curves are everywhere. But he asked this question, are they really everywhere? And he makes very persuasive arguments to claim that actually many other distributions are very often masquerading or masking themselves as bell curves, right? In real life. So it is not as you think. So let's use the word symmetric. Given a symmetric distribution, what can you tell about A versus C? How do they differ?
They're stressed on one side.
That's right. So I'll give you a mnemonic to remember. Whenever you see this, think of a duck. You know, we love ducks and cows. Think of a duck. Think of this as the beak of a duck. And give it an eye. Right? In A, duck A is looking towards right or left? Guys, speak up. Which way is A looking? The duck A.
Right.
The duck is looking towards the right. What? Positive direction. This is negative direction or positive direction. What about this? The middle guy. This is a hard duck. It's not looking anywhere, isn't it? It's probably looking at you, right? What about the duck C? It's looking
Left.
looking left or negative direction. Would you agree with this? Simple, right? Convention being this is positive, this is negative in a coordinate system. So you say that it turns out magically that this curve, you say, has positive or right skew. And this guy has negative or left, these words are used interchangeably, skew. And this has no skew, it's symmetric. By definition, symmetry is the opposite of skew, right? Skew breaks symmetry. You don't have symmetry. Are we making sense? And it turns out that your k is equal to 3, the third standardized moment, is literally the mathematical expression that will quantify how much the skew is. Lovely, isn't it?
So all you have to do is just k is equal to 3
In that
equation,
equation.
that's it.
That is
You
it.
don't have to worry about the entire
Just
equation.
take the z values and raise it to the third power and find its expectation value, you will get the skew. Are we together? Now, what about the fourth power? If third one has some interpretation, maybe the fourth one also has some interpretation. It turns out the fourth one also has a name. It is called kurtosis. What in the world does kurtosis measure? It turns out what it measured, people had a pretty strong debate about. There were many interpretations of what the fourth moment meant, fourth standardized moment meant intuitively. What in the world is it measuring? Remember, it's a statistic. What exactly is the meaning of this statistic? So there were many interpretations, but I think the final word came around 2014, as recently, when somebody pointed out a very simple intuition. He said that, see, if you take the fourth power of anything, so suppose you have z1 fourth power plus z2 fourth power, zn. So let me just put two z's here for zi to the fourth power, zj to the fourth power, and zn to the fourth power. Some of these numbers are bigger than the other. Now, in your mind, and these are all deviations from the normal, from the mean, isn't it? So what will happen for a value that is close to the mean, an inliner data point, relatively close to the mean? Its power could be, let's say that it is 3 units away from the mean. So 3 to the power 4. And let's say that another unit is an outlier. Outlier means it is 100 units away from the mean, right? So 100 to the power 4. Now, guys, try to right? And by the way, so okay, so there is one more catch to it. I said z values, so z values won't take 3 values. So let me take it this way. I apologize. Z values, what happens is they take values from -3 to +3. +3s are outliers, right? Most values are close to 0. Why? Because you did xi minus mu over sigma. You scaled it, the data, right? Zi, sorry, I should have been careful. So suppose the mean is 6.4. Look at your data. And did anyone compute the standard deviation, guys? In the data set that we considered a little bit ago? You can find the standard deviation is what, approximately 3? Could somebody please plug it in and check in the computer? If I have to guesstimate, I would say, let's say the standard deviation is 3. Right. So for each of the values, if you look at this, for this 7 minus 6.4, which is the mean, divided by 3, right, is 0.6 divided by 3 is 0.2. Right. This would be 3.4 divided by 3 is 1.1. Do you see that these are all small values, isn't it? These values are small. But if you have an outlier, its value will be like more like 3, 4. Extreme outliers, 2.5. Those are outliers. Because outliers, and this is a fact, take it as a fact, that most inliners have values in this interval, close to 0. Right, fractional values. So what will happen when you take a fractional number, even 0.9, and you take the 4th power of it? Let's take that. This is 0.9 to the 4th power. And this happens to be, let's say 3 to the 4th power. And this happens to be 0.1 to the 4th power. Right? You realize that this will practically disappear. Right? And this will become 0. Something like 64, isn't it? Approximately 65 or something like that. And this 3 to the power 4. 3 square is 9. 9 square is 81. Right? So what is happening? This value overwhelms all the other values. You might as well ignore the smaller values, and you may just look at the outlier values. Right? Look mostly at outliers, looks mostly at outliers. Right? So if there are no outliers, the kurtosis will be small. If they are big outliers, kurtosis will be big. Right? Some people call it the heavy tail effect. Like if the tail is heavy, lots of outliers are there, big heavy tail. Right? Heavy tail. Some people call it heavy tail. Means there are lots of outliers sitting there. Then that is measured by high kurtosis. High kurtosis tells you how significantly outliers are present in your data. And as you know, we live in the world of long tail distributions. Like, for example, most books don't sell much, but some books go on selling gazillions of copies. Right?
So this is called
kurtosis.
high tail.
Yeah, heavy tail.
Heavy
tail. Right? So guys, we introduce you to many descriptive statistics today. And this is the only class on statistics that we'll have. We will use this now to actually make progress in the next 45 minutes. So guys, from a perspective, the core idea is start with the Z value. It is the core, standardize the data, right? You wake up in the morning, brush your teeth, look at the data, and you go standardize it. Right? Sort of think of it like that. You must do it. Most of the time you should do it. Right? Sometimes you need not do it. Sometimes it may even be counterproductive, but that's rare. But this is it. Then there is a concept of expectation value. Expectation value is essentially averaging that power, right? For discrete numbers. For continuous, you have to bring in a distribution. We'll forget about it. Now we realize that there is this concept, mu k and sigma k, but ultimately what it comes to is the ratio. The ratio is mu k over sigma k. A little bit complicated mathematical expressions, but basically in simplest terms, the kth moment, standardized moment, is expectation value of the zk. right? That is one easy way to remember it, right? The average of the kth powers.
So Asif, you said k is equal to 4 is
Kurtosis.
and what about k is equal to 3?
Skewness. Skew is k is equal to 3 and kurtosis is k is equal to 4. K is equal to 3. A third moment. So now you see the usefulness of the concept of moments, isn't it? So each moment describes something. Now what the fifth moment describes, I have no idea. But if you figure out the interpretation, let me know. But it is a descriptive. I can't put away, obvious intuition on it, but I'm sure people have tried and I may just be ignorant. I may just not be knowing about it. So this is statistics, guys, right? Now comes a final result in statistic that we'll use. And it's about the only last piece of statistic. It is a profound result. It's a crown jewel of statistics. It's called the center limit theorem. Center limit theorem. So guys, I'll do this and then we'll take a break and then we'll start with the machine learning proper. Center limit theorem says that for me to explain the center limit theorem, I need to create the concept of a probability distribution. Right? So there's a concept called probability distribution or probability density, let's say. Density distribution. The density is implicit. Wow, that's a big, big word. But I call it one bucket of sand. Right? So suppose you have one bucket of sand, you spread it like this. You put it on the x-axis, right? Whatever values your random variables can take. For example, height, well, cannot be 0 for human beings. Let's say the height starts at, I don't know, 1 foot for people, babies, and goes up to what, 8 foot? Who knows? Something like this. This is your range. So then the more people you find at a given point, at a given height value, let's say 5 feet, 5.5 feet, the more grains of sand you put there. So what happens is as you keep distributing the sand, and remember you have only one bucket of sand to put. So what you will, so here is one way to do it. You first create the histogram. You know what a frequency plot is? Every time you find a human being, put a value there and then create a frequency plot and then make sure that your sample size is very, very large. So you get some distribution like this. Now divided by the number of people. So suppose here you had access like, okay, at this height, I found 9 million people out of, let's say, 20 million. I'm just taking some random numbers, 25 million population, sample size, n is equal to this. So one rough way that people do is when sample sizes are large, you can divide this value, each of these height things, divide by n. When you divide by n, you scale down all of them, right? So each of them becomes a fraction, right? And so what happens is that you end up with something called a probability density distribution. It's as simple as that, right? So you end up with some distribution and these values will never go up to 1. In fact, the area under it will be 1. The area px dx will be 1, right? Or if you look at discrete values, the summation of all of these pxi's will be 1 based on discrete or continuous. So which makes sense, right? So let's say that people come in only 2 sizes, 3 foot and 6 foot. Let's take an example. 3 foot people, there are 20 of them. 6 foot people, there are 10 of them, right? So would it be fair to say that the you draw a histogram and 30 foot is 20, and this is 10. 3 feet, 6 feet. These are only two values, right? 20, 10. If I divide it by the total, what will I get? I will get, what is the total? N is equal to 30. 2/3 and 1/3, right? 3 feet, 1 feet. Would it be fair to say that these numbers represent the probability if you randomly picked a human being? 2/3 probability that it will be 3 feet, the person will be 3 feet, isn't it? And 1/3 the probability that the person would be 6 foot. Would that be fair to say that? Right? It would be fair. And so what you have done is whenever you convert a histogram, you normalize it by dividing by n, you get a probability. You get probabilities. In continuous form, you get explicit, I mean, in discrete form, you get explicit values. Now generalize it to continuous, right? So you get probability density. So now here is one intuition that I have. The fact that the area under the curve, or the fact that they all need to add up to 1, I look at it this way. You get 1 bucket of sand. You need to distribute it fairly to be representative of the data. So children make little sand piles, isn't it? You made a sand pile and a sand pile, but your total sand pile has to be the 1 unit of 1 bucket of sand, right? Likewise, height of people in reality is not just these two values, is spread over a space, whatever the min-max range is. You would agree that the area under this, the probability of finding a particular height xi, if I integrate over all of the xi values, right? This of course has to be 1, right? It's because I have 1 unit sand. I'm just spreading it around. So if you think of probability density is a way 1 bucket of sand is spread, that's actually a powerful intuition. And when we go deep into machine learning and we are talking about such things as Wasserstein distance and Wasserstein-Gann. Actually, those of you who attended my ML100 must be familiar with these words I used. They all derive their intuition from this. In fact, Wasserstein distance is if I have a pile of sand that looks like this and a pile of sand that looks like differently, how much material do I have to shift to go from A to B? It is called the optimal transport problem. There are many ways I can do it. The bad ways would be take all the sand, first put it in 1 bucket, in 1 giant pile, and then spread it to look like this. Bad idea. Because this shape, A and B, they approximately look alike. You want to just move in the minimum amount of sand to make A transition into B. That's sort of the optimal. It's a big theory, by the way. It's one of the hottest topics these days. Optimal transport. And so Wasserstein distance measures how different are two distributions, right? And so forth. So we'll keep that for later, but at this moment we do that, probability distribution. So now we come to our crown jewel for today, which is the center limit theorem. And for statistics, the moment you see the beauty and power of it, it will completely astound you, right? So let me bring that, and then we'll talk about biased and unbiased estimators. So there's a very interesting thing. No matter the distribution of your data, whether it is like this, whether it is symmetric, whether it is like this, right? Whether it is like this, doesn't matter, whichever way you look. So this is your underlying distribution of the data, whatever it is. For example, if you look at the income of people in your company, it looks like this, by the way. Most of us are common, ordinary people. We earn within a range. And then there are the rich executives, right? Or the upper management, which earn somewhere here, in US at least. Right? So, well, this, by the way, is a fact. This is well studied in economics. So there are many distributions of data. But here is something. You take a sample of people, any sample, and we will start with the average, the mean. So you take sample S1, it will have a mean mu1. You take sample S2, it will have a mean mu2. You take sample S3, it will have a mean S3. Now you realize that each of your samples can be pretty biased. right? For example, so let's take one curve, any one curve. I'll just deliberately take the curve that skewed, that is, do you see the skew? Maybe I'll make the skew even more pronounced. That is like this. Okay, you agree that this doesn't look symmetric? I'll make it even more unsymmetric. How about this? Right. And this hill, I'll make it smooth. I'm trying to make it look different on the two sides. Would you agree that they look different on the two sides? Or did I end up making something symmetric? Hopefully not, right? So now, or maybe let's make it pronouncedly like this. Okay, how about this? This is very asymmetric.
That represents.
The probability distribution of some random variable x. Height of people. What is the probability that people are of this height? Think of the histogram, simply
The three
put.
samples are going to give that probability distribution.
So basically, if you took the whole population and you measured their heights, right, they will look like they will look like a histogram similar to this, up to a scale, right? That's one way of thinking about it, right? Or in this particular case, if you look at a very, very, very large company of employees, right, IBM or something like that, or then their salary distribution, let's say, may look like this, right? Yeah, probability distribution, as I said, up to a scale is essentially histogram. Right now, here's one interesting thing. You take some random people. They may have been, it turns out that by accident, the data is biased. You ended up going to upper management. You ended up on the wrong floor of the corporate building. And they are all sitting there sipping their lattes, right? And preparing for their champagnes in the evening or while they're discussing some, I don't know, big things. I'm joking, right? And then by chance, another time you ended up on a second floor where all the minions are there, like us, drones, working at it. And then somebody goes and gets a sample that is spread out like this. So you realize that if you take the mean, the means will not be true means because you know that the samples are biased, or you put in no effort to make unbiased samples. Are we together? Just go take random samples. And if you just by happen chance, there will always be some bias in the samples. Would you agree, guys? Remotely, those of you who are there, you would agree that there'll be some bias in the samples. So if you compute their means, you don't really expect their means to be correct representation of the entire population, isn't it? The means wouldn't represent the whole population, would it, guys?
No.
No, it wouldn't. You say, because each of the means is biased because you expect the data underneath to be biased. But here comes a beautiful, beautiful fact of statistics, the center limit theorem. It says no matter what the underlying distribution is, I'll say this because this statement needs to be spelled out. No matter how the underlying distribution, probability distribution, let me write the word prop distribution looks. Can I use a more intuitive word, data distribution? How the data is distributed? Distribution looks. All the mu i's, so you know your mu1, mu2, mu 1000, right? If you plot the mean, if you just plot the mu's, you will notice something absolutely beautiful emerge. Unbelievably, they will all have a beautiful, the mu's will have a beautiful bell curve distribution. This is it. All the mu's will collectively bell curve. Well, the formal word is normal distribution. Now think for a moment how amazing it is. You can start with all sorts of weird distributions, but if you keep sampling data from that distribution or take little samples of the data of the population, those mu's will form a bell curve. And the next amazing fact is that the peak, now in a bell curve, what happens? The mean, median, mode are the same. Mean, median, mode are the same. It's a very interesting distribution, isn't it? The most frequent, the median, and the average are the same. This value will actually tend to the population true mean. Isn't that amazing? Yeah, the effective mean of the means will be the true mean of the population, however crazy the distribution. Now, what is the intuition behind it? See, each sample has a bias. It introduces an error in the mean, right? But those errors tend to cancel each other out. And so you end up with a mu. The mean of means is close to the population mean. That is the center limit theorem. Now I'll pause here because I just introduced you to something called an unbiased estimator. What in the world is an unbiased estimator? If you go through this process, mu, mean, we say is an unbiased estimator. In other words, the mu of mu, the average of the samples, will tend to be pretty good representation of the population mean. Are we together? Right. So this is estimator, means estimate. A mean is an estimation. Think of it as a statistic. It's an unbiased statistic. Are we together? Because it will tell you the right answer. But then why are we making such a big deal about this mean and its unbiasedness? It turns out it's not true for other things. For example, if you look at variance, there is a problem with variance. The problem with variance is that, let's say that the underlying distribution is whatever. Again, go to the same distribution. Do you realize that the variance of all of this is limited, right? The variance measures the variability, but if every time you take a small sample, its variability will be less than that of the population, isn't it? Almost always, the value of variance will be less than that of the population. This population variance will be greater than any of the sample variances, isn't
So
it?
we're assuming that we're not taking random samples because
No, you're
when
taking
it's
random
random,
samples. But if you take random samples, you're very unlikely to always hit the tail points. With a sufficiently large
yes.
population, you're unlikely to hit the tail points. You will hit some, you'll pick up some points from in between somewhere, right? You're not likely to pick up all the tail points in such a way that the variance of the sample will be the same as the variance of the population. So the point is, the sample variances will always be smaller than the population variance. So what do you say? If they are always smaller, then you can go about averaging the variances, but will they ever represent the true variance of the population? No, because each of the values is smaller than the real population variance. Guys, are we following me? The variance of the variance square of the standard deviation, or just just look at the picture. If each of the variance is smaller than the population, let's say that sigma 1, let's say square is less than the actual, let me just call it population sigma variance. Sigma 2 also is less than sigma population squared, so on and so forth. So when I add all of them and average, you would agree that this will still remain much smaller than the population variance. It's not going to change, right? So what have we done? Samples will always underestimate the variance. Does this fact come through, guys? right? And so what happens is, while the definition, so what happens is that, so now comes a fact, guys. When you take a sufficiently big sample, right? Sufficiently big sample, or you take a sample of sample, like you take the mean of samples, irrespective, mu will be unbiased. The mean of sample will be reflective of population mean, more or less, up to a error bar, right? But sigma square, and therefore sigma standard deviation, will be sample will always underestimate population variance, population sigma, isn't it? Sigma square of the population. That's quite an interesting fact, just thinking about it, isn't it? You say, therefore, that variance is a biased estimator. This is now you understand why we say mean is unbiased when you look at samples, because just looking at a good enough sample, you get a good sense of the mean. But looking at a sample, you don't get a good sense of the variance. Do you see that? Right? This is biased when you're looking at the sample. So what happens is that for variance, and therefore for standard deviation, there is actually, people have figured out, and the reasons are a bit mathematical, we won't go into, for a population, for all data, population, let's say that you line up all of humanity together, right? Then you know that there is no bias, ultimately is the population. So sigma population squared would be the average of the xi minus mu squared, the average of them. That makes sense, isn't it? Oh, I forgot my summation symbol. Actually, let me write it neatly. That's because these are nodes. So this makes sense, guys? Right? This is literally the definition as you learned in the school books. Trouble is, in machine learning and data science, most of the time we have only samples. All right. So for samples, sigma sample square is, and here is the thing, you realize that it underestimates. So instead of dividing by n, what people do is they divide by n minus 1. Now n minus 1 will be a smaller denominator, means the value increases or decreases? Increases. So what you do is, when you're dealing with sample, you just boost it a little bit. You boost it a little bit, and it turns out that this is just the right amount of boosting. Boosting. So n goes to n minus 1, boosting to make sigma sample. People say it's make it unbiased, close to unbiased. It's unbiased, right? Right? Or more representative, or more representative of the population. So you're acknowledging that no matter what, when you take a sample, there are always things on this or that side of the sample, quite often, right? So I mean of the sample in the population. So it's a biased estimator, variance. You should remember that. So these terms keep coming up, biased and unbiased estimator, and so on and so forth. So we have covered a large statistical territory today, guys. I notice it's 10 past 10. So I would like to finish it. Today is the only time we will do statistics, and we are done. As I said, we were flying rather fast. We were in a Concorde, isn't it? And in a Concorde, we flew over the entire descriptive statistical land, right? And we found some remarkable things. Let's see what we learned today. In a more formal sense, we learned about, where did we start? We learned of the concept of what is a statistic. Like when you say chemistry, you don't say chemistries, but when you study statistics, it always comes as a plural. So now you know, because a statistic is a measure, a description of the data, right? Data. We talked about population and sample. A data set could be either the population or a sample of the population. Samples can be biased or unbiased, right? When it is unbiased, it's representative of the data. Small samples are almost never representative of the data for the simple reason that how would you, it's very hard to make, like for example, if you pick only 2 people to measure the average height of humanity, are you likely to get a good sense of the humanity's height? No, right? So take a large enough sample and try your level best to be as unbiased as you can in the sample. But more than that, people have realized that taking more samples is better. Take lots of samples, don't just take one sample, right? Take lots of samples because there, center limit theorem is your friend. We talked about z-value or standardization of the data. We learned about, once you have standardization, we understood what variance means, what mean means, what mode means. Variance is just literally the spread, right? So a basic example is when you have kids, right? When the kid is sleeping, all the toys are in a pile, low variance. Then the kid wakes up and toys are all over the room. They're all spread out, high variance, right? This is it. If you look at the the coordinates along any one of the walls, they're not all over the place, right? They're spread out. That is variance of the data. So the z-value is pretty root, and at the end of the day, there's a concept of movement, standardized movements, but the standardized movement is essentially comes from your z-value in simplified form. It's the powers of the z-value, first, second, third, fourth. The third is skewness. What in the world is skewness? It shows which way your distribution is bending, right? Is it looking right? If you always think of your distributions as ducks. Which way is the duck looking? The beak. If the beak is going in the positive direction, it's right skewed. Or in the right direction, it's right skewed. If it is going in the left direction, it's left or negatively skewed. And if the duck is staring straight at you, it's symmetric, right? Now, it turns out that all this mathematical gymnastics that we did beautifully relates to our intuition of skew. It turns out it measures to what extent or which direction is the duck looking. If you want to know that, look at the third standardized moment. Then comes kurtosis, which is like how spread out or outliers they are in the data. It is not about skew, but the outliers or the quantity of outliers there, or how heavy the tails are. That is the kurtosis. It's the fourth moment of the data. Then we learned about the fact, this remarkable thing in statistics, a crown jewel. And guys, the more you think about this center limit theorem, the more awestruck you would be at its sheer elegance and power. It shows its presence just about everywhere. Read about it, that's your homework. Learn more about it. We'll do a lab or so about it. You take, what it says is something absolutely remarkable. It says, however crazy your distribution or however crazily you have put the sand, right? You spread out the sand, and you can do it in multiple dimensions, but crazy looking sand castles you have built with that one bucket of sand doesn't matter. If you take lots of samples and you keep taking their mean, those mean values will form a bell curve, number one, and the mean of that bell curve would be the true mean of the population, irrespective of the distribution. Very, very insightful thing. Then, oh, by the way, I did not mention to you one extra thing about the skewness, and I would like to do that. See, what happens is, look at this. Where is the mode? In a right skew, where is the mode? This is the mode. Right? where is the mean? Because it has a long tail, the mean is here, isn't it? And where is the median value? Somewhere here. So in a right skew, mode is less than median is less than mean, right? In this way. In a left skew, the opposite will be true. Mode is here. Let me use green colors. Mode is here. The mean will be here. It's symmetric, right? It is just the mirror symmetry of this, and this is the median. Right? So mean will be greater than median is greater than mode. Mode. Right? No, hang on. What did I do wrong? No. Mean is less than. Sorry, what silly thing I did. Mean is less than the mode, as you can see in this picture here. Right. So this is just a fact as I'm summarizing for today.
Asif, also about the expression for covariance and correlation.
We'll take it up to next time, because we'll take it as part of the linear regression. We're intimately connected. So we'll do it next time. Today, I think, would you guys be willing to stay another hour? No.
So covariance and what next?
No, of course not. Covariance and correlation, the mathematical thing, because that gets into linear regression. So regression and covariance correlation, the mathematics is next time. So the beautiful thing is you can center limit theorem, guys, please go study it. It's a crown jewel, right? Economics. I know one economist in India, there's this economist who has written quite a few books, Haricharan Das or somebody, India Unbound. If you have read those books. So I think it was him or somebody else who said when he first learned of the center limit theorem in his MBA, he just rushed to the library because he couldn't believe that something like this could be true.
So that's all you require, right? Center limit theorem. You don't require the other things that you discussed.
No.
No, mu of mu, right?
So now the unbiased. So mean we consider unbiased estimator, because with sufficiently large sample size or with a sample of with a lot of sample sizes, lots of samples is always better. You have the power of center limit with you. The estimates you'll get will be unbiased, means your sample estimates will reflect your population estimates, but not so for variance, for reasons that we showed. Variances will always be less than the population variance. So one way to compensate is you put this n-1. See, guys, you may have wondered why in books of data science, when you open it up, you find this n-1. So now you know why. Right?
There's also a nomenclature difference between actual population versus.
Yeah, people use different symbols, but I'm just using sigma sample and sigma population. Right? So with that, guys, we end today. I'll keep maybe 10 minutes for QA. Any questions, guys? Was it all overwhelming? Did the Concord go very fast, or was it?
Does this mean they're ready for one of the quizzes?
No, correlation. We still have to wait for correlation, causation, the correlation and covariance. All right, guys. I don't know how many of you are still with me.
Asif, why it's only n-1? Why it can't be n-2 or n-3?
I give that to you as a homework.
Okay. Does it do anything have to do with degrees of freedom?
I'm not answering.
Okay, got it.
Asif, one question.
Go ahead.
Will the mean of the variance, sample variance,
Yeah.
collective population variance?
No, it will always be less than if each of the variance is less than the population. So the mean of the variance will also be less than the population.
Okay.
So that is why it's called a biased estimator, right? Because variances, samples never tell you about the correct variance. And so you can correct it a little bit by changing the denominator, by sort of shrinking the denominator a little bit. to boost the value, to boost the variance up a little bit. It turns out that is just the right amount of it if you do n-1, assuming a reasonably good sample size. Huh? That's that. So why it is? Go ahead, Hina.
Do we do n-1 to give leeway to the last sample that it will compensate
no, nothing
variance?
No, there is not a last element. It isn't like that. It isn't like that. The cause is not that. But why don't you guys take that as a homework? Find out why n-1. Why not n-100 or n- whatever, right? Or why not something else? Why n-1? I'll leave that as a homework for you to figure out.
And Asif, is there any way to know like how much sample size is big enough from, let's say, I know the population size?
So jocular way of saying no sample size is big enough. But in real life, you work with whatever sample size you get. See, guys, here's the thing. When you deal with physical data, engineering data, often you have lots of data. You have the luxury of taking large sample sizes. But in domains like rare diseases, sample sizes are like 5, right? And you are supposed to infer something with 5 patients, right? You know that it's too small a sample, but beggars can't be choosers. Or as in my school, somebody used to say, if beggars were horses, what is it? If wishes were horses, beggars would ride. Right? So if you can wish for more data, but unfortunately, real life situation is many times you don't have enough data. So you should ask for the biggest sample size and sort of compromise with whatever you get. Does that answer you, Hari?
Yeah, I thought there is some mathematical formula where you can determine, okay, these many number of sizes.
Here's
Okay.
the heuristic that I use. For sufficiently large population sizes, I tend to take the square root of n.
Okay, square root of
Minimum threshold for myself. So suppose you're talking about people and there are 10,000 of them.
Yeah.
I would not make any definitive statements without lot of cautionary statements about bias, unless I had at least 100 fairly random samples, representative 100 people or 100 items, data instances.
Ways to calculate how big your sample needs to be.
Yeah, there are. So here's the thing, guys. There are some techniques. There's some heuristics, some ways of looking at it. But I would say that in real life, in practical life, you should try to get the biggest sample that you can get your hand on. But then we live in the world of big data. It doesn't mean that you chomp through a petabyte of data saying, now I have a big enough sample. That brings us to other aspects, the real life computational aspect. And there are algorithms. For example, you can find the median of a vast population of data without actually calculating the median or looking at it, right? So there's the Boyer-Moore theorem and so on and so forth methods. They're lovely algorithms in machine learning, which are specific to big data. Someday we'll talk about it.
I think for small size data, for central limit theorem to apply, at least it needs to be minimum of 30 samples, right? And
yeah, people do say, see, Kyle, those are numbers. Those are heuristic. You can't put a magic number. These are experience talking. Common sense says that below 30, what will you do? Right? It doesn't, how would you, like, if you have only 30 data points, how many samples, frankly, can you take out of it? How much bootstrapping can you do, right? So you often sample from the sample. That's a reality. So we'll come to all these topics, bootstrapping and so forth in due time. It's one of the topics, but let's again learn to walk before we run.
Hey Asif, can you please explain the usage of probability mass function and how it differs from the density one?
Yes, see, what did we do? Look at this case of people who have only 2 heights, 3 feet, 6 feet. So remember, we made 2 sand pillars. First of all, we made a histogram 20 and 30, 20 and 10, isn't it? Then when we divided it by 30, total number of people, we got 2/3 and 1/3, discrete numbers, isn't it? We put 2/3 of the sand at 3 feet. We put 1/3 of the sand at 6 feet. Let me mark it as 6 feet, isn't it?
Yeah.
This is probability mass function. But when values are continuous, in reality, people don't come in just 2 sizes. Only clothes come in 2 sizes or 3 sizes. Human beings come with a spectrum of weight and our height, and our height keeps changing, isn't it? Over we grow, we shrink. Certainly with weight, we grow and shrink all the time, right? So when it is a continuous distribution, it is a probability density. So continuous is density. Discrete is mass.
Okay.
That's it. That's the difference between the two. So Siddhartha and Ankur, how did you?
Area under the curve for both of them would
No, for mass function, these are discrete blocks, right? Like with sand, imagine you're sitting at the beach and making discrete pillars, right? But for continuous variable, it's literally as nicely making a hill of various shapes. That is the probability density. So this is density, mass, probability mass, probability density.
So the area under the curve for both would be 1.
Area under the curve will be by definition. So look here, in the histogram, there were 30 people, 23 feet, 10, 6 feet. If I divide it by the total, I get the proportion. In simple terms, proportion is probability, right? When you look at it, proportion is probability. So two-third proportion of people are 3 feet. So therefore, probability of, if you randomly pick a guy and ask how tall he is going to be, 3 feet or 6 feet, you would say 2/3 chance that he'll be 3 feet, 1/3 chance that he'll be 6 feet. Does that agree with your intuition, Hina? Yeah, that is it. Now take it to continuous domain, generalize, add different values. Now, what would happen if you had 3.5? And just think of these as very tiny, tiny little pillars sitting here, right? With values between this, and so forth. All right, guys, anybody else? Any question before we end?
Yeah.
Go ahead.
Yes. If so, in Galton's paper, I read one statement which said that daughter's height is mostly dependent on father's height, and son's height is mostly dependent on mother's height. Like, he did not give any proof, but he made that statement after that 1.7, and he.
Yeah, no, there are many nuggets in that paper, but for our case, we will focus only on the regression towards the mean.
Okay.
But he does have certain observations like that. I don't know whether they were later validated or not. Maybe they were. So why don't you do that? You have the data. Dalton data is available. I believe it's one of our homeworks. You can see how closely that is true. Maybe it's true. Almost surely it's true. Now, Dalton's student was, guess who? It was Pearson, the guy who created the definition of correlation. And so our next topic will be Pearson.
Okay, got it.
All right, guys. If no one else is asking questions, we'll stop. Siddharth and Ankur, please stay back.